case I ever teach this class again. But we'll see if that happens, because I doubt it. Alright. Huh?
Said, I don't know, you might get some ambitious students.
Well, it's not just ambitious students. Because remember what we have to do with calculus as well.
That's true. You mean how we went over trade and whatnot?
No, how we did calculus first and then physics.
We had to do
That's right.
a week.
And making that work into academy schedule, it's not necessarily going to work. And I wouldn't teach this as a co-requisite for calculus. That'd be a lot easier. But you really need calculus ahead of time. You can't do them both at the same time.
Yeah.
And anyone who goes through the material understands that, but the people I have to convince of that fact aren't convinced of that fact. Because they don't know the material.
That's fair.
Alright, so today will be our first day on the last section of our book. And the last 4 chapters here are going to be about thermodynamics. Thermodynamics, the dynamics of thermoactivity. Basically, we're studying heat and properties of heat in the next 4 chapters. And we introduce finally a new metric, temperature. So up until now, everything we've been talking about has been one of 4 fundamental units. We've either been talking about lengths, which we measure with meters. We've been talking about time, which we measure with seconds. We've been talking about mass, which we measure with kilograms. And now finally we're introducing temperature today.
Okay.
And we'll typically use Kelvin in talking about temperature. But you've also heard of Fahrenheit and Celsius.
So in our calculations, we'll be using Kelvin.
Kelvin will be the most natural to use.
Okay.
Although Celsius is also used quite a bit because Kelvin and Celsius count the same way. But point being, we're now introducing a 4th fundamental unit that we actually go out there and measure, temperature. And temperature is something different from mass or from speed or length. Watts, remember, was joules per second.
What about joules?
Joules are energy, which is force times distance. What was force? Mass times acceleration. So here's the units of force, kilogram meters per second squared, times it by a distance. Now we have energy, divided by seconds. Now we have watts, and those are the units of watts. And so it's just been combinations of these things thus far.
Yes. Are we going to make more combinations with temperature now?
So now we'll be introducing a new metric that we actually measure, something we go out there and measure, temperature. And we'll talk more about that as we get into the actual material. But before we get into the material, the problem is that the author presupposes that you guys have high school chemistry, which, since you're in high school, half of you haven't taken high school chemistry.
Yeah.
And so we need to do a review of some basic chemistry that we're going to need for these next 4 sections. And so I'm going to do a run through some basic chemistry, and almost everything I'm going to tell you is going to be an oversimplification. I'm going to lie to you a lot to give you the right intuition. Okay? All right. So fundamentally, all the matter in this universe that we interact with is composed of molecules, sure. And those molecules are
Atoms.
atoms, and atoms are composed of
Protons, neutrons.
protons, neutrons, and electrons. So fundamentally, the matter that we see in the universe is protons, and I'll symbolize protons like this, a circle with a plus on it. Protons are positively charged. A neutron I'll draw like this, just an empty circle. And an electron I'll draw like this, an E with a minus sign right there. Why do I draw them like that? I have no clue. Probably because of electric chemistry. That's how my teacher did it. That's all simplified. Protons, neutrons, electrons. Protons are positively charged, electrons are negatively charged. Neutrons have no charge. Negative charges attract, like charges repel. A proton and an electron have the same magnitude of charge, it's just opposite charges. So if I have a proton right next to an electron, and I come stand over here, the charge I feel is 0.
Yes.
Because they perfectly cancel each other out. Whereas if I put 2 protons here and 1 electron, and I stand over here, now I'll measure a positive charge. I'll feel a positive charge. Because one electron can't cancel out two protons. It only cancels out one proton.
Isn't the mass of a proton a lot bigger than?
Not talking about mass, talking about charge. We'll get to mass here in a second.
Don't matter with charge?
Nothing to do with the charge.
Okay.
Okay. So electrons and protons, they have the exact same charge, just opposite charges. It has the exact same strength. You can kind of think about it like the gravitational force on me and the floor's normal force. The normal force is that way, my weight is that way. Those are exactly the same force, just opposite directions.
Yes.
So the force from a plus from one proton and the force from an electron are identical in strength, just opposite directions. If a proton pushes you that way, an electron's pulling you that way, if we have a charged particle here, with the exact same force.
Say that again?
Imagine I'm holding a charged particle right here.
Positive or negative?
Doesn't matter, pick one.
Okay.
If it's positively charged, then however hard the proton is pushing it that way, the electron is pulling it that way the exact same hard. And so it's not moving. But if I got rid of the electron and I'm holding a positive charge here, now it's going to shoot off that way.
Yeah.
Okay? So protons and electrons have the exact same charge, just opposite directions. Exact same magnitude of charge. The strength of their charge is identical.
Okay.
With me?
Mm-hmm.
Okay. So now let's try to physically imagine how these things look. Imagine we shrink you down and now you're actually looking at a proton, a neutron, an electron. And let's say that you zoom down so a proton looks this big, and we'll imagine them as a big ball. Here's a proton. So if a proton looks this big, how big does a neutron look? It looks roughly the exact same size, a neutron. How big does an electron look? Teeny. Has less than 1,000th the mass as either of these.
Yeah.
So relative to the size of a proton or a neutron, an electron is teeny. It's absurdly small.
Okay.
Make sense?
Mm-hmm.
Has roughly 1,000th, has less than 1,000th the mass. Okay, but roughly 1/1000th. Really rough. So now we can take protons, neutrons, and electrons and we can stick them together in stable configurations. And those stable configurations we call an atom.
Okay.
So the simplest atom is a hydrogen atom. What does a hydrogen atom look like? It has a proton at its center, and then it has an electron on the outside, and we think about the electrons as orbiting around the protons. Oversimplification, but how we think about it. So here's a stable atom configuration. We have one proton, one electron, so the whole charge on this thing is 0. And we view the electron as just orbiting the proton.
What about a neutron?
Simplest case right here. That's as simple as we can get it. One proton, one electron. That's the simplest atom there is.
Okay.
And we call that thing hydrogen. We call it hydrogen because it has one proton.
Yeah.
Naturally.
Next most common atom in the universe, so this is the most common atom in the universe, hydrogen. The next most common is helium. Helium, its nucleus is made up of 2 protons, 2 neutrons, and then it has 2 electrons orbiting around. That's a helium atom. Now, well, we'll specify that in a second, but now let me ask you a question. Roughly speaking, how much bigger is a hydrogen atom than a helium atom?
4 times?
It's going to have roughly 4 times the mass,
Yeah.
right? Wonderful. And then lithium, I don't know how many neutrons lithium typically has. I think it has 3. But so a lithium atom, don't trust my picture here too much. A lithium atom then typically a lithium atom has 3 protons. And I think typically 3 neutrons, not positive there, but then 3 electrons orbiting around it.
Yes.
Lithium atom. A lithium atom is roughly 6 times as massive as a hydrogen atom.
Is it the third most common atom?
Yes, it's the 3rd most common atom in the universe. Hydrogen, helium, and lithium are the most common. And I can't remember the percentages, but it's like this thing makes up like 97%, this makes up like 2.9%, and this makes up like 0.01% of the matter in the universe that we interact with. And then everything else takes up like 0.001% or whatever it is. So now you have a periodic table, or you've seen a periodic table before. You recall the periodic table of an element. What's an element? It's a type of atom. So this is an atom, this is an atom, this is an atom. This thing's element is hydrogen, this thing's element is helium, this thing's element is lithium. And we could go on and we could talk about beryllium, boron, carbon, whatever. Naming out all the atoms on your periodic table. Now what defines an atom, how do I determine if I were to draw a picture of some random atom, how would you determine what type of atom it was, what element it was?
The amount of protons.
Strictly by the amount of protons. If it has one proton, by definition, it's hydrogen. If it has two protons, by definition, it's helium. So if I were to take this and throw on another neutron, it's still a helium atom.
Yes.
This is just typically how most helium atoms in the universe exist.
Okay.
Some might have an extra neutron on there. Some might have a neutron missing, but most of them look like this. This is how most hydrogen atoms in the universe look. Some of them have a neutron on there. The majority of them are just a single hydrogen atom.
Is neutron like just dead weight?
A neutron?
Like how does a neutron get connected to a proton?
We're not going to talk about the strong nuclear force.
Okay.
They stick together.
They stick together.
They stick together. When you get protons and neutrons really, really close together, they stick.
Does it matter if there's more electrons?
Notice what happens if there's more electrons. So if we have another electron here, then these two electrons by themselves kind of cancel out these two protons. And so now there's nothing really holding this electron in. And so if some positive charge comes along, it'll suck it off. Because you can kind of think about, again, way oversimplification, but you can kind of think about as this is keeping this in orbit and this is keeping this in orbit. And now that's all can guarantee to keep in orbit. Putting more electrons there, yeah, you can stick it there, but it's not very stable and it will probably wander off. So in general, most are stable atoms, they have as many electrons as they have protons. Make sense? Okay, so now to the important topic, a mole. So think about a hydrogen atom for a second. And remember that if we say that this thing has roughly a weight of 1, then a helium atom has roughly a weight of 4. And a lithium atom has roughly a weight of 6. Right? Okay. So now let me ask you a question. Imagine I've got some scale inside of a vacuum, and I stick a hydrogen atom on the scale, and I stick another hydrogen atom on the scale, and I stick another hydrogen atom on the scale, and I'm going to weigh these things. How many hydrogen atoms do I have to stick on that scale so I finally measure 1 gram of hydrogen?
A billion.
A billion, a trillion,
A mole.
1 mole. So 1 mole is equal to, now I remember what it is. It's like 6.11 times 10 to the 23.
Yeah.
It's a little bit bigger than a billion.
A little bit bigger than a billion. I know that we have to have it in our book somewhere.
I'm sure it's in the table in the
In the table on the back.
good it's just
Yeah, see if you can Google it real quick. I can't use my phone since I'm recording. But it's going to be a number roughly like this. So 1 mole is how many hydrogen atoms I need to get 1 gram of hydrogen.
Does the mole change on the atom?
No, it's just a number. So if 1 mole of hydrogen weighs 1 gram, then 1 mole of helium weighs
4 grams?
4 grams, right? Look, if 100 of these weighed 1 gram, then 100 of these is going to weigh 4 grams. If 1 mole of these weighs 1 gram, then 1 mole of these weighs 4 grams. Go ahead.
6.022 times 10 to
6.022 times 10 to the 23?
Yep.
Not bad.
Yeah, you were not that bad.
Okay, so there's the actual mole number. But you got the important part. A mole is just a number. How much does a mole of lithium weigh? 6 grams. Right?
And you can tell that by the amount of protons.
And neutrons.
How do you know how many neutrons there
So now when you look on a periodic table of elements, and I don't know, do we have a periodic table in our book?
Yeah.
Yep.
Is that the front or the back?
Back.
Before the answers to the odds?
I think so.
Yes. Wonderful. So when we look on a periodic table, I'll pick a random one. I'll just find our spot book. So I'll pick a random one. Plutonium. Okay. That's Pa, right? I think Pa is plutonium.
I think so.
Oh no, that's Pu. Pu is plutonium. So Pu, plutonium, when you look at it, plutonium is the 94th element. And then you'll also see a number at the bottom of plutonium, which is 244, like that.
Okay.
And, well, good enough. Okay, so 94 is its atomic number. That means plutonium atoms have 94 protons.
Okay.
This is its atomic weight. Its atomic weight is how much 1 mole weighs in grams. Or in other words, a plutonium atom has 94 protons, and it has, what would that be? 150 neutrons. So it has 150 neutrons. What's 150 plus 94?
244.
244, which is its atomic weight. So hydrogen is 1, and it has an atomic weight of 1. Helium is 2, and it has an atomic weight of 4. 4 is basically the count of its protons and neutrons.
Yeah.
And you can double check lithium now. Lithium is 3, and its atomic weight is actually 7. So lithium actually has an extra neutron on there. So 3, we have lithium, and its atomic weight is 7.
But these are just generalities, right? Usually has 4.
Usually has. Perfect. Which takes us to our next point. When you actually go and look up lithium, you're not going to see a 7 here. Instead, you're going to see a 6.941.
So that accounts for the...
And that accounts for the fact that most of them have 7, but occasionally you get one that only has 6.
Yeah.
Does the...
And so chances are, if you take 1 mole of them, since like 5% of them are going to only have 3 neutrons, and then the other 95% are going to have 4 neutrons, then chances are when you take 1 mole of that material, which is a ton, then this is the actual weight that you're going to get. Does that make sense?
Yeah.
Okay, so that's why these numbers aren't perfectly rounded off numbers.
Yeah, that makes sense.
But those are moles.
This is its atomic weight. This is how much 1 mole of this element would weigh in grams. What's 1 mole? It's how many hydrogen atoms I need to get 1 gram of hydrogen.
So that tells you the amount of neutrons.
Yes, it tells you on average how many neutrons and protons these things have. Because the electrons hardly add to the weight.
Yeah.
If you were dealing with however big a mole is, wouldn't that deal with the weight too of an electron?
The weight of an electron may have a slight impact on this number. Maybe if we didn't count the electrons, then that would put like a 0 right there.
Well, even then, it probably wouldn't do that much.
Well, I don't know.
It's
1,000. Maybe it would even affect this. So yeah, maybe these numbers are accounting for the electrons as well. giving you intuition for where these numbers come from. So you should be able to guess right out the door that helium's atomic weight is 4. When you go actually look it up, helium's atomic weight is 4.003. Okay, so that's the important thing that you're going to need to know in this section.
Atomic weight.
How to get the mass. If I tell you that you have 2 moles of hydrogen, what's the mass of the gas that you're dealing with?
2 grams.
2 grams.
Okay.
You're going to be able to understand things like that. Go back and forth between talking about the mass of a gas versus how many actual atoms are in that gas.
Oh, I see.
Because notice that if I have some gas canister and I go and I weigh it, and say the gas canister is full of oxygen, and I go and I weigh it, and I find out, okay, this gas, when it's full of oxygen, weighs an extra 1 kilogram, right?
Okay.
I can figure out how many actual oxygen molecules are in that thing.
Yeah, you can.
Now, oxygen gas, you might not know this, but oxygen is just an oxygen double bonded with another oxygen. So an actual oxygen that you breathe in is actually 2 oxygen atoms hooked together. You don't breathe in just pure oxygen atoms by themselves. They're 2 hooked together.
Mm-hmm.
Does that make sense?
Mm-hmm.
And so, if I know I have 1 kilogram of molecules that look like this, I can find the atomic weight of this thing. So I look up, what's the atomic weight of oxygen? 16. So the atomic weight of an oxygen molecule is going to be 32. So I know 1 mole of this gives me 32 grams.
Yes.
And then so I calculate how many moles would give me 1 kilogram. Or let's just keep it simple. Let's say that the gas canister weighs 64 grams when it's full. So when my gas canister is full of oxygen gas, it weighs 64 grams more than it did before. Okay, then I know that that canister is containing 2 moles of those molecules.
Of those molecules, which is
Yes.
4 moles of oxygen.
4 moles of oxygen, but the point is I can count how many actual molecules are bouncing around in there.
Yeah.
That's the amazing part. And you could go now do the same thing for water. Water, you know, is H2O.
Mm-hmm.
So it's a H bonded with an O, bonded with an H,
It's
H2O.
double bond.
Yeah, because you have the electron of this thing, and
But it only has 1 electron. Yeah.
1. Okay. So a water molecule, right there, atomic weight of 1, atomic weight of 16, atomic weight of 1, that has an atomic weight of 18. 1 mole of this weighs 18 grams. You can go fill up a bucket until you have 18 grams of water in there, and you can calculate how many actual water molecules you have in that thing.
And why is
Yeah.
water so heavy?
They're really condensed together. 18 grams of water, I mean, to get 18 grams of air, I might need this much air, whereas 18 grams of water, I only need this much water for it to be 18 grams.
Yeah.
So the atoms are the molecules are much more compact in water than they are in air.
Does it matter if you do an equal sign versus a minus sign?
Yeah. That's not what they mean.
That's not what they mean. Sorry. We won't talk about the electrons. This isn't a chemistry class. Doesn't matter. It was just to help me think better these pictures. Okay, forget that. But you know, should just on this. H2O, there's your water. Okay, 2 hydrogens, 1 oxygen. And so it has an atomic weight of 18.
Yep.
And so 1 mole of water weighs 18 grams. If you have 32 grams of water, you know how many actual water molecules you're talking about. And you could actually calculate how many hydrogen atoms and how many oxygen atoms are in there.
Yeah.
So I could give you a glass of water and ask you, calculate how many hydrogen atoms are in this glass. And you could do that.
Why is that?
That sounds like you're going to put it on the test.
Because now you can figure out exactly how many atoms something is composed of. Think about how absurd that is. You can calculate how many atoms are in your glass of water.
Without even seeing them.
By measuring the water inside.
By just measuring the mass of the water.
How do you measure the mass of water?
You put on a scale. 1 kilogram of water produces a 1 Newton force. Now I can't remember how to convert from newtons to pounds, but there's a way to do it. You've done it. Okay, so that is our quick crash course in chemistry that we need. I just realized I probably went off the recording when I drew over there. You guys can't let me do that.
Not a lot.
Huh?
Not a lot.
Not a lot?
Just.
Let me go past that line. Okay. Anyways, so there was a quick crash course on chemistry to give you intuition for what a mole is, because we're going to need to understand it. Okay. So now starting actual chapter 17.
Do you always want to round up when you use the atomic weight? Or round?
Do you always want to round when what?
You use an atomic weight. Like, is hydrogen like slightly more, so it wouldn't be 18, it would be like 18.006.
Yeah, I was just rounding. I mean, do what makes sense for your problem. If you're doing a problem and they give you 6 significant figures for all your other numbers, then yeah, use all significant figures you can from your periodic table.
Okay.
In general, the more figures you use, the better. It's not going to hurt you to use more. Okay. So now starting today's material. In today's material, we start out with the 0th law of thermodynamics. The 0th law of thermodynamics. Yes, the 0th because it was discovered after the first or second law of thermodynamics.
Why doesn't that make it the third?
Because it's what fundamentally underlies all of thermodynamics. And so it's the one you need to cover first.
So why not just bump the other two up and call that one first?
Because that would confuse everyone for historical purposes.
So the 0.
It's the same reason that we can't decide from now on an inch is just going to be 1/10 of a foot. None of this 1/12 nonsense. No, you throw everyone into whack when you do that. Everyone understands it one way, you got to stick with it.
Yeah, that makes sense.
So when you say 0, it's 0 with a DTH.
The 0th.
Or just TH. 0.
Yes, the 0th law of thermodynamics. Okay, what is the 0th law of thermodynamics? So let's say we have some system A, some system B, and some system C, all in contact with each other.
System being what?
A, B, C. They could be blocks of ice, they could be chairs, they could be anything. Some systems in contact with each other.
Okay.
I think system C is supposed to be the middle one to make it read correctly. So system C, system B. And then I'll just read the words directly, and then we'll make sense of it.
Okay.
So if C is initially in thermal equilibrium with both A and B, then A and B are also in thermal equilibrium with each other. This result is called the 0th law of thermodynamics. If C is initially in equilibrium with both A and B, then A and B are in thermal equilibrium with each other.
What's equilibrium?
So thermal equilibrium means they're the same temperature.
Same temperature?
Same temperature. Okay, 0th law of thermodynamics. If this is the same temperature as this, and this, it's going to sound obvious now when we say it this way.
Yeah.
Another way we can say thermal equilibrium is no heat is being transferred back and forth anymore. So, two systems are in thermal equilibrium if and only if they have the same temperature, or two systems are in thermal equilibrium if they're no longer transferring heat between each other. There's no more net transfer of heat. And so the 0th law of thermodynamics says that if C is in thermal equilibrium with these two systems, then these two systems are also in thermal equilibrium with each other. Which seems pretty obvious, right?
Yeah, that makes sense.
Okay, thermal equilibrium. And so how do we test if systems are in thermal equilibrium? We measure their temperature. measure their temperature with a thermometer. Now the units that we use for temperature, we have 3 different units that we're used to using. We're used to using Fahrenheit, we're used to using Celsius, and then we're used to using, well, you're probably not used to using Kelvin, but those are the 3 units that we have for measuring temperature. And to give you a rough idea, let's talk about just Fahrenheit and Celsius for a second. We'll come back to Kelvin later. Fahrenheit and Celsius for a second. What's the freezing point of water at Fahrenheit?
32.
32 degrees Fahrenheit. And then what's the boiling point of water?
212.
212. 212 degrees. Perfect. So Fahrenheit was the first units that we started using, and then eventually we came along and we said, let's use Celsius instead. How did these numbers come into being? Why 32 and 212?
Yeah.
I can't remember the exact story that accompanies this anymore, but it was roughly that 32 degrees, or that 0 degrees for the man who discovered this, Fahrenheit, or who invented this scale. It was like he made 0 degrees the coldest condition he could produce in his lab, which just, and then I can't remember what he picked for his 100.
His 100?
Yeah. So he picked like, I'm not positive what it is, I'm making stuff up right now. But like 0 degrees was, he chose 0 degrees to be the coldest condition he could produce in his lab, and then maybe 100 degrees was the hottest condition he could produce in his lab. Evenly divide that up, and then it just so happens that 32 degrees is the temperature that water freezes at, and 212 degrees
Temperature water boils at.
is the temperature water boils at. And these are just coincidences based on his scale.
I see, that makes sense.
Okay. Then we said, that's done. Let's come up with a better scale. And so we came up with the Celsius scale. How does the Celsius scale work? We chose 0 degrees to be the freezing point of water, and we chose 100 degrees to be the boiling point of water at sea level.
Yes.
How convenient.
Yeah, so we did that by choice, and then you evenly divide up all the temperatures in between into 100 pieces.
Yeah.
And then everything else falls where everything else falls. And so that's how Fahrenheit and Celsius came into existence. Now, what we're going to be interested in doing is converting between Fahrenheit and Celsius all the time. And I don't know which way they give you the equation first. Temperature in Fahrenheit from temperature in Celsius. So, here's our equation. Temperature in Fahrenheit is equal to 32 plus 5/9 temperature in Celsius. Did I do that right? Or is it 9/5?
Mm.
9/5. Okay, that's right. I guess I can double check with my book. Make sure my logic's right. Yeah, they just write in the other order, so I'll follow their order, which makes sense. So 9/5, your temperature in Celsius plus 32 gives you your temperature in Fahrenheit.
Yeah, that makes sense.
So when we plug in 0 degrees for our temperature in Celsius, what do we get in Fahrenheit?
32?
When we plug in 100 degrees, what do we get Fahrenheit?
I assume it's 212.
You can do that in your head. 100 divided by 5
20.
times 9
180.
plus 32.
Oh. Okay.
Wonderful. And then temperature in Celsius, obviously, we just solved this thing for TC now. So that is going to be 5/9 your temperature Fahrenheit minus 32.
Okay.
And don't lose track of those parentheses. They definitely matter. Because when you solve for TC in this equation, what do? First you subtract 32 over here, and then you times both sides by 5/9.
Yeah.
Which just undoes it. Okay, so that's how we go back and forth between units. Now, Kelvin. How do we talk about Kelvin? So a type of thermometer that we use is measuring the pressure of a gas. So I have some gas right here, and then some bar right here to conduct some conductor of temperature right there.
Yeah.
And then I have some pressure gauge on this thing so I can read the pressure of the gas inside of here.
Okay.
And there's gas inside. So when I stick this bar right here in something hot, then it heats up this whole material, which heats up the gas inside. Heating up the gas inside increases the pressure,
Yes.
which then creates, if I measure the pressure, then when I increase the temperature, the pressure goes up until I measure the temperature rising.
Yeah.
And if it cools down, the gas jiggles less, the pressure goes down, and the pressure I measure decreases, and so the temperature I measure decreases. So this is one of the ways that we measure temperature.
Through pressure?
Through pressure. A pressure thermometer is one of the things that we use to measure temperature.
Okay.
Another way that we often measure temperature, you're used to seeing, is just like a regular thermometer. A regular thermometer that you're used to seeing, there's some liquid in there like mercury. And as mercury heats up, it expands. And as mercury cools down, it contracts.
Yeah.
So I have a teeny bit of mercury inside of some tube. Right?
Yes.
So here's some tube. I go and I stick that tube in a freezer or whatever, some place where I have control over the temperature, where it's at freezing point, and maybe the mercury only fills up this high in my tube. So then I know that, okay, that's 0. I go stick my thermometer now in boiling water. The mercury then expands up to this point, so I go and I mark that on the glass as 100, and then I evenly divide up all the spaces between.
Pretty straightforward.
And now I can create my temperature as high this way as I want, because I now know what a 1 is, and I can create it down that way as much as I want.
Okay.
But let's go back to now the pressure thermometer instead, because we noticed something interesting with a pressure thermometer. So depending on the gas that we put in here,
Okay.
then different temperatures are going to create different pressures. The same way that depending on what you put in your tube, when you create a homemade thermometer, putting mercury in there, when you heat up mercury, it expands a lot more than if you would have filled it up with steel. When you heat up steel, it only expands a little. When you heat up mercury, it expands a lot. Yeah, metal.
Steel.
How much does a metal rod heat up when you stick it in a freezer? How much does a metal rod expand?
A lot.
Hardly any.
Yeah.
Go stick it in boiling water, how much does it expand? Not very much at all. Mercury expands a lot.
What other liquids can you use?
Doesn't matter. The point is, different liquids expand at different rates for the same temperature.
Yeah.
Okay. Similarly, different gases produce different pressures for the same temperature.
Okay.
Okay. So what did we do? We noticed something strange. So we'll say that this is here we're measuring pressure, here we're measuring temperature. So for a given pressure, we got some given temperature. And so we noticed for different thermometers like this, at 0 degrees Celsius, we had some had a pressure here, others had like a pressure there. And maybe others had like a pressure up here. And then when we went over to 100 degrees Celsius, maybe it looked more like this. Something like that. But we noticed that if you run the system backwards, and I didn't draw this very good, so I'll redraw those dots. So maybe for one of our thermometers, measuring the pressure here, so here we're measuring the pressure. The pressure at 0 for this one was this, the pressure at 0 for this one was this, the pressure at 0 for this one was this, and then at 100 it was this. And someone started plotting these things out, and they noticed that all these lines for hundreds of different ones all seem to come together at this same point, where the pressure would be 0.
Oh, absolute 0.
Which is where absolute 0 comes from. And if you measure, let's pretend that this was in Celsius, and if you were to count backwards, then this would be on the scale negative 273.15 degrees Celsius.
Yes, that's right.
So for all these different systems, if we would cool them down to this temperature, the pressure inside of there would now be 0. And the temperature that produces 0 pressure, we call absolute 0. We now call this absolute 0. You with me?
Mm-hmm.
And so on our Kelvin scale, it starts counting 0 here. This is 0 degrees Kelvin. And Kelvin has the same increments as Celsius.
That's right.
The same.
The same increment as Celsius. They just have different zeros. What they call 0 is different. If I were to heat up the temperature in this room by 1 degree Fahrenheit, that's less than if I were to heat up the temperature in this room by 1 degree Celsius.
Mm-hmm.
However, if I were to heat up this room by 1 degree Celsius, or I were to heat it up by 1 degree Kelvin, that would be the same change in temperature.
Okay.
So the only difference between Celsius and Kelvin is what they call 0. Celsius calls 0 at the freezing point of water. Kelvin calls 0 at absolute 0. And so 0 degrees Celsius is actually 273.15 degrees Kelvin.
So Kelvin has no negatives.
Kelvin has no negatives.
Okay.
Okay, so on our Kelvin scale, this would be 273.15. And then this one right here would be 373.15. What can I do for you?
Can Peter come to the office for just a minute?
He sure can. Since he knows all this already.
You won't be missing anything.
Okay, so our temperature in Kelvin then is equal to our temperature in Celsius plus 273.15. And let me double check that 273.15. Yes, that's correct.
Okay.
Okay. Maybe we could do a quick example while he's gone. You place a small piece of ice in your mouth. Eventually the water all converts from ice, which is 32 degrees Fahrenheit, to body temperature, which is 98.6 degrees Fahrenheit. Express these temperatures in both Celsius, degrees, and kelvins. Okay, so we've got some ice. So our temperature in Fahrenheit initially is equal to 32, they say 0.00 degrees Fahrenheit. Well, I'll just call it T1. T2 is equal to 98.60 degrees Fahrenheit. You're used to that number.
Mm-hmm.
Anything higher than that, you're considered to have a fever. Right? That's your natural body temperature. Anyways, and so what is the change in temperature here?
Change in temperature?
Yeah. So we're looking for, I think that's what we're calculating. We're calculating the change in temperature, but expressing it in terms of degrees and Celsius. So maybe let's rewrite T1 really quick in terms of Celsius. So what's T1 in terms of Celsius?
Just 0 degrees.
Just 0 degrees Celsius. 0 degrees Celsius. And T2 is, we don't know.
Yeah.
And so now we have to calculate it. Hopefully I remember to grab my calculator. And so, express it 98.6 degrees Fahrenheit in terms of Celsius. We're going to use this equation right here. So I take 98.6 and I subtract 32 from it. And then I take that number and I multiply it by 5/9. And we get 37. So this is 37 degrees Celsius.
Okay.
Yeah.
Now, what's T1 in terms of Kelvin?
273.15.
273.15. Kelvin. And we actually don't say degrees Kelvin, it's just Kelvin. So there's no little circle there, there's just a K. And then our T2 in terms of Kelvin is then what?
310.
0.15.
Wait, 1, yeah.
310.15 Kelvin. Okay, now our job was to calculate the temperature difference in terms of Celsius and then in terms of Kelvin. So in terms of Celsius, what's my temperature difference? What's delta T?
37.
37 degrees Celsius. And then what's delta T in Kelvin?
37 degrees.
37.
37 Kelvin.
So the only difference between them is what they call their zeros. And so I think that's what they were trying to hit home with this. Oh, I guess they also wanted to calculate the delta T in terms of Fahrenheit. If we express it in terms of Fahrenheit, what do we get?
Get 64 or 66.
0.6.
0.6.
Okay, so there we go. That was the first example. I don't know, we really need to stress that point. Something that they want to stress for you. Going back to thinking about our thermometer here. Our thermometer, it all falls out from the equation that we're about to use, that we're going to use. So an equation that we're going to use, we'll introduce later, is that pressure times volume is equal to N, the number of atoms we're using, times R times T, the temperature. So we're going to get to this equation eventually. May as well get used to it right now. Get used to thinking about this equation.
What's the equation called again?
Uh,
Pressure equation?
I could have just said it 10 seconds ago, and now I can't. Ideal gas formula, something like that. Okay, anyways, notice that if volume, let me really quick put volume N and R all on one side and PT on the other side. So then I get pressure over temperature is equal to N over R times V, or divided by V, right?
What's the R?
R is a constant, N is the number of molecules that we have, and V is the volume.
Number of molecules. How would you get that?
From its mass. We just barely talked about that. How you can now count the number of water molecules inside a glass of water.
So what's the... Okay. Yeah.
Okay? R is just a constant, V is the volume. So notice going back to our thermometer here, our pressure thermometer. Our pressure thermometer had some gas enclosed in this still container. Right?
Mm-hmm.
And so no atoms could escape from this pressure thermometer. They're all stuck inside of there. And they also can't occupy any more space. Their volume is fixed.
Yes.
Right?
Mm-hmm.
So notice that with this thermometer, V is fixed, N is fixed, and R is already a constant. So this whole side is a constant.
So V stands for volume, right?
V stands for volume.
Okay.
So your pressure over your temperature always has to be a constant with a thermometer like this.
Pressure over temperature.
Yeah.
And that's saying... What does that number represent?
Over here.
Yeah.
That represents pressure, that represents temperature. It's just a relationship for a second. Notice that in this system, the only quantities that can change are the temperature and the pressure. I can't change the volume, and I can't change the number of atoms in there. So this whole side now acts like a constant in this special case.
Oh, so once you find temperature, you can find pressure?
Once you find temperature, you can find pressure, but the point is, pressure over temperature is equal to a constant.
So when you...
So if we were to calculate this number, and this whole number right here for this system comes out 10, whatever. Some number, 10. Then I know that pressure over temperature, no matter what the pressure and temperature are, those can change, is always equal to 10. some constant.
Yeah.
So that means my pressure, measure my pressure and temperature at time 1, P1 and T1, measure again at some future time, P2, T2, then those have to be equal. Because they're equal to the same constant.
Yes. Okay.
So this is the equation that they give you. They try to walk you through the intuition. I think it's easier to jump to the equation and then explain that. So that's a formula you're going to get. You don't really need to memorize that because once you get this formula, this is a relationship you get for free. Because this only applies in that special scenario where the volume and the number of molecules that you're talking about are fixed. Okay, so now we're ready to go back and talk about something that we've already talked a bit about. Thermal expansion.
Thermal expansion.
Oh, we didn't talk about thermal expansion yet, did we?
No.
No, we talked about pulling on something to stretch it.
Yeah.
Sorry. Confuse those two sometimes. Okay, so we've talked about the notion of if I take a steel rod and I pull on it, it stretches a little bit. Well, another way I can stretch a steel rod is I take it and I just heat it up and it expands a little bit. And you're used to this. Common scenario, a jar lid that you can't open. What do?
Run it under hot water.
Why?
Heats it
Because
up.
it expands the.
It actually expands the lid. So the lid is tighter around the glass. When you heat it up, the lid expands a little bit. And so it's looser around the glass. And so you can take it off.
So if
You
it's
do
frozen,
this with pipes as well, right? If it, like a funny pipe and it doesn't quite fit, then you would heat it up.
You can heat it up, stick it on, and then let it cool down. And it creates a really good grip.
Yeah.
So it's something that we utilize a lot in engineering. Engineers utilize this fact a lot, heat something up to put it on there, let it cool down, and then it creates a very tight seal.
Do they ever freeze stuff just to make it tighter?
Freeze it to make it tighter? I don't know. It'd eventually warm up again.
Yeah.
Probably. I mean, I would guess yes. There's just so many use cases that there's no way I can know even a small fraction of them. So, I would guess yes, I just don't know of any case.
Okay.
Anyway, so thermal expansion. Things heat up, they expand, things cool down, they contract. As a general rule. There's a couple exceptions to that rule. You're very familiar with one exception to that rule. So weirdest property about this material that you deal with all the time, you practically drink it in, yeah, water. Water is the exception to the rule.
Because it gets bigger when it freezes.
For some reason, water, it does both. If I've got water, as I cool water down, it gets smaller and smaller and smaller and smaller and smaller and smaller until it starts expanding.
Yeah.
And so if I were to plot water with respect to temperature, plot its volume with respect to temperature, so here's the volume some water is occupying, here's its temperature, it looks like this. And the place where you get it the coldest is at 4 degrees Celsius.
Which would be what? 40 degrees?
It doesn't really shoot off like that forever. 4 degrees Celsius. The point is, by the time it gets to 0 degrees Celsius, where it freezes, you know that ice expands.
Why is 4 before 0?
4 degrees.
Oh, I was thinking about it as we cool it down. So my scale's backwards. Here's 100 degrees Celsius. Sorry, I have no clue why my brain thought about it that way. Here's 4 degrees Celsius. Here's 0 degrees Celsius. That is weird that I thought about it that way. But in general, the more you heat it up, the more it expands, right? And you keep heating it up, water eventually expands to steam. Steam occupies a lot more space than water.
Yeah.
But when you condense it to the point where you get ice, it actually expands again, which is very strange. The majority of materials in this universe do not behave this way.
So why does
Water
this-
is a very strange exception.
Don't liquids do that?
No. No. Water does that. It seems like a normal thing because water does it and we're so used to water, but no, water is weird. Water is like the only thing that you come across in your day-to-day life that behaves this way. Everything else behaves normally. If I were to take this calculator and I were to melt it, so now we just have it converted to a liquid form, the liquid would occupy more volume than the actual calculator. Now, if I kept heating it up to the point where it was a gas, assuming everything in there could become a gas, it would occupy more space.
And if you kept freezing, it would just get smaller and smaller.
To some limiting point.
Just minimum. There is a minimum.
Yeah, everything has to occupy some space.
Is there a minimum point on that expansion?
For a gas,
For heat, for when you heat it up.
a gas kind of just naturally expands unless it's in some sort of container.
So it doesn't.
Huh?
So it doesn't have a minimum from expansion.
I don't know how to talk about a maximum volume that a gas can occupy.
Okay.
Because I mean, put some box and say we only have one gas atom in there, and it just keeps bouncing around.
Yeah.
So you have one atom, is it filling up the box? Our notions of a gas filling up when you get that sparse kind of breaks down. These are very high level terms that we're using, and they're not very precise. What does it mean for a gas to occupy this much volume? It only makes sense if you don't look too closely. The volume that this thing occupies, it only makes sense if you don't look too closely. The closer you look, the more our notion of volume breaks down.
Yeah.
So, that's it. Okay, so thermal expansion. As a general rule, throw water out the window, forget about water. Everything else in the universe, not everything, but most things in the universe, they expand as they heat up. And so we can express their new length, their change in length, so delta L is going to be proportional to two things. First off, just to guide your intuition for what I'm about to write, if I've got some, let's say I've got some metal rod or something like that, I don't know. I've got some metal rod, and I heat it up by an extra 100 degrees Celsius, and it expands an inch.
Okay.
How much would I expect it to expand if I heated it up an extra 200 degrees Celsius?
2 inches then?
Probably 2 inches, right? If I double my temperature change, I probably double my change in length.
How does it make any sense?
Okay, let's go back to symbol.
I mean,
Here's my metal rod at 100 degrees Celsius.
Okay.
Let's say at 101 degrees Celsius, it now grew that much.
Okay.
At 102 degrees Celsius, what would I expect? I'd expect it to grow by that much again. Right? Or maybe instead of 100 degrees Celsius, let's say that this was 100 degrees Celsius, this was 200 degrees Celsius, and this was 300 degrees Celsius. I don't know.
So if you just kept going to like 1,000,
As we heat it up more and more, it expands more and more.
you could almost double its length.
Well, it's eventually going to break down, because eventually I'm going to heat it so much, it's not a metal rod anymore. It becomes a liquid.
Yeah.
And if I heat it up too much after that, it becomes a gas. And all the atoms are just shooting off in every direction. So this is only going to work under small temperature changes, so maybe we shouldn't say that. Maybe we should say 100, 101, 102. And let's just pretend that those were really, really zoomed in. Because obviously it doesn't grow by that much. It grows by a teeny fraction of that. I can't draw how much it grows. But when I have a metal rod and I heat it up 1 degree Celsius, it grows a teeny bit, right?
So you're saying it's all linear.
It's linear. We would expect, the more we change the temperature, we would expect our change in temperature to be directly proportional to our change in length,
Yeah, that makes sense.
right? So whatever our change in length is, we would expect the more you change the temperature, the more you change the length. Second thing, if I've got some metal rod, so I've got a meter-long metal rod, and let's say when I heat it up by 10 degrees Celsius, it expands a centimeter. So 1 meter expands 1 centimeter when I heat it up 10 degrees.
Yes.
Let's say at the same time I also had a 2 meter long metal rod, and I heated it up by the same much. How much would we expect it to expand?
2 centimeters.
2 centimeters. So we also expect this to be directly proportional to its initial length, which all signifies L.
Oh, so length does matter.
So length does matter. Length matters, temperature matters. And then finally, not all materials expand to temperature the same. Some expand more than others. So we would also expect some sort of alpha, some sort of constant that changes depending on what material we're talking about. And that's our change in length formula. Alpha L naught delta T. So let me write it the way that they have it actually. Alpha L naught being the initial length, delta T. Follow that formula?
Mm-hmm.
Okay. Now, we could do a similar thing for our, well, maybe specifying. So this alpha now depends on the material. And so when you were to calculate the change in length, given some change in temperature, you'd have to go look up in a table what this alpha was, right?
Yes.
That makes sense? Okay, so now what about changes in volumes? Because you also get change in volume when you heat up a material.
Well, it would just be the same,
It would be very similar. Our change in volume would equal some constant, beta, times our initial volume, times our change in temperature. Something like that.
Oh, yeah, that makes sense.
Now you're going to know something, and also the betas you go and you look up in tables and you're going to see them in tables. And you're going to notice something interesting about beta relative to alpha. So if I go look up in my table alpha for a, let's see, one that's easy to expand out, brass. So alpha for brass, alpha of brass is equal to, now I forgot the number, 2.0 times 10 to the negative 5. 2.0 times 10 to the negative 5. When I go look up beta for brass, I'm going to know something very strange. It's going to be 6.0 times 10 to the negative 5. It's going to be 6 times what alpha was, or 3 times what alpha was.
Well, that makes sense.
That does?
Yeah, because alpha is just in one direction, but beta is in 3 directions.
So it's not the cube of it? Shouldn't it be alpha times alpha times alpha?
No? No, because it's linear. Or am I thinking about it weird?
Okay. So this relationship shouldn't be completely obvious to you. It should be a little bit strange that this is happening. And so let's show exactly where this is coming from. So we have this equation and we have this equation. If I were to make an infinitesimal change in length from an infinitesimal change in temperature, we'd represent that this way. An infinitesimal change in length would be alpha times L naught times an infinitesimal change in temperature, right?
Yes.
Mm-hmm.
And similarly, we could rewrite this equation this way. Beta times V naught times dV. Now, I think I want to start with just what is volume. So volume is going to be equal to length cubed.
Okay. Yeah.
Good so far?
Yeah.
Okay. So our derivative of volume with respect to length is going to be equal to 3L squared, like that.
Yes.
Or in other words, dV is equal to 3L squared dl. I could also write it like that, right? Now this is true in general, no matter what. This gives me the change in volume at some specific length. Maybe look at this one. This one says, give me a specific length, and here's your change in volume with respect to length, right?
Yes.
So we want our change in volume when our length is L naught. So I'm just going to rewrite. So this is true in general for our specific case. So we're actually looking at something, some cube, where our side lengths here are L naught, and L naught. And so our volume is actually V naught, which is L naught cubed. You with me?
Mm-hmm.
So for our specific case, I'm going to rewrite it this way. dV is equal to 3L naught squared dL. Right?
Oh, and then you make.
That's just for our specific case.
Okay.
Now substitute dL in our specific case in right here. So dV is equal to 3L naught squared times alpha times L naught times dt.
So 3 alpha.
L naught squared times L naught is
L naught,
V
yeah.
naught, right?
V naught, yes.
So dV is equal to, well, let's move our alpha over here. So we have 3 alpha times L naught squared times L naught is L naught cubed times dt. And we get 3 alpha there.
Yeah.
And we rename that 3 alpha beta, and that's where this equation comes from. So that's why beta is exactly 3 alpha for materials that show up in both places. Some places we can't really talk about their linear length, but we can still talk about their change in volume. You can't talk about the length of water, but water still expands when you heat it up.
Yeah, that makes sense.
Okay. So that's why there's that relationship. Let's see, should we do examples or continue? This is kind of on the same vein, so we'll continue kind of on the same thing and then go back to examples. So let's imagine some scenario now where I've got some metal rod and it's attached at two ends to immovable objects. You with me?
Mm-hmm.
Now, let's say that I hook up this rod when it's like 100 degrees Celsius. I don't know. I know it's super hot, but just for the sake of helping you understand. So let's say we hook up this rod in conditions where it's 100 degrees Celsius.
Okay.
And now we go and we take the system and we go and we put it outside, and now the system's outside. And outside the temperature is now 30 degrees Celsius. And so the temperature drops a considerable amount. What's going to happen?
The width is going to shrink.
The rod wants to contract in on itself.
Yes. But it can't.
But it can't, because it's being held in place. And so we create this stress in the rod. And if we were to overstress it, the system would actually break.
Oh, so it's not shrinking in width, it's just stressed?
It's going to stress the rod, which could produce it to get somewhat skinnier. But it's the exact same thing as if you just take a metal rod and pull really hard on either end. Right?
Yes.
The metal rod wants to be this big. We're forcing it to be this big. So we must be pulling it really, really hard.
Yeah.
Or a similar thing could happen. Let's say that we produce the rod in conditions that we set up the rod in conditions that were 30 degrees Celsius, and now it's 100 degrees Celsius, and so now the rod wants to expand, but we won't let it. We're compressing it in. Right? So as we change the temperature, this creates thermal stress in our system. We call it thermal stress. As it heats up and cools down, it creates stress in our system. And so engineers, when they're doing things like building bridges, they need to be very aware of this fact.
Yeah, that makes sense.
Because on your coldest days, I mean a bridge, I don't know the coldest that it gets in terms of Celsius, but it probably goes an average range of somewhere between, it probably has an overall difference of like 50 degrees Celsius that it needs to be able to handle. Something like that. And so they have to keep this in mind. And so let's actually calculate that stress and strain. And so to do this, we're going to go back and remind ourselves of Young's modulus. Young's modulus was equal to force over area divided by our change in length over L naught, our initial length. Is this ringing bells?
Yeah.
Or if we were to solve this for delta L over L naught, delta L over L naught is equal to F over A times Young's modulus.
Young's modulus is like stress.
Young's modulus is a constant based off of the material. It relates the stress in the system to the change in length produced.
Oh, so force over area is stress?
Yes.
Okay.
We can also think about that as pressure.
Oh, yeah.
Stress is like internal pressure in the system.
How did you get it?
Did I do it wrong?
Why is the delta L still over L naught when you moved it to the other side?
I moved this over here and this down here.
Oh, yeah.
So that's right, right?
Yeah.
Yes.
Okay. And now notice from this equation, I can also write delta L over L naught is equal to alpha times delta T.
Where did you get that?
Just move the L naught over here.
Oh, I see.
Okay. So notice what these two equations are saying. This equation tells us the proportional change in my length given a certain stress in the system.
Yes.
This gives me the proportional change in length given a certain change in temperature in my system.
So stress and temperature are related?
So change in temperature, to keep a system, so now let's go back and talk about our system. Here's our rod. And we'll only talk about this end for a second. And let's talk about the two scenarios going on here. I don't know, do we want to talk about when we're heating it up or cooling it down?
Heating it up.
Heating it up. So when we're heating it up, then this is producing, our temperature is trying to produce a positive change in length, right?
Yes.
So it's like the temperature is trying to get it to expand, so the temperature is trying to push this end out that way further.
Mm-hmm.
So the system then, if it's going to contain it, has to counter that out with a force this way.
How does it create that force that way?
Because it's hooked to the wall. Whatever the wall is pushing back, won't let it expand.
Oh,
Whatever it is.
yeah.
So the point is, then if temperature is trying to expand the rod, then stress and strain is trying to contract the rod. And so my change in length, we'll call this my change in length from stress, and we'll call this my change in length from temperature. The point is, my change in length from temperature plus my change in length from stress always has to equal 0. If my temperature is trying to expand the system, then the stress is contracting the system.
Yes, that makes sense.
On the other hand, if I were cooling it down, so my temperature change is trying to has a negative delta L, is trying to shrink it, then my stress and strain is stretching it, and so it's going to have a positive delta L. So the sign of the delta L here is going to be opposite the sign of the delta L here. If one's expanding, then one's contracting. If one's contracting, then one's expanding. They're going to have opposite signs.
Thermal stress, right?
Yes. The thermal stress produced here is going to counteract, well, this is what we mean by the thermal stress. The stress that is used to keep the system in check. Because if it just heats up, there's no thermal stress. If I don't have the walls here and the bar can just expand, there's no thermal stress.
Yeah.
So thermal stress is a stress that's produced to counter out the thermal expansion.
Okay.
That's a better way to say it. So if my change in length from stress and strain plus my change in length, if my change in length from temperature plus my change in length from stress is always equal to 0, well, this is also equal to, what's delta L over L naught from my temperature? That's equal to alpha plus delta T, or alpha times delta T, plus my change in length from my stress is F over AY. That has to be equal to 0. right? Because my total change in length has to be 0.
Yeah, that makes sense.
And so finally, if we solve this for F over A, then we get F over A is equal to negative alpha times Young's modulus times delta T. And so here is the amount of stress produced for a given temperature change in a system.
The amount of stress.
Yeah, force over area gives you stress. So it's the amount of stress produced in a system given a certain temperature change.
So
if I know that my bridge is going to undergo a maximum temperature change of 50 degrees Celsius, then I know the max thermal stress and strain that I need the bridge to be able to handle.
Oh. So engineers use this all the time.
Engineers use this all the time.
Gotcha. That's pretty cool.
We take into account thermal expansion all the time in the way we design things. You've noticed on the sidewalks that were poured intelligently, then there's gaps filled in with a wood liquid material that can easily be smashed because the sidewalk is going to expand and contract throughout the year. And you'll notice that people who weren't paying very close enough attention to when they were pouring it, the sidewalk goes like that, and there's all these places on the sidewalk that tip up like that and make a point. And that's someone who doesn't know what they're doing, didn't do their job right, didn't take into account thermal expansion correctly.
Yeah, that makes sense.
Right? Or if you have ever been over like a bridge, particularly a bridge that can raise or go down, then you'll notice that where it connects, you'll see some teeth like this on one side, and you'll see teeth like this on the other side. And you might get a little bit disturbed that those aren't actually touching each other.
Because it allows for expansion.
Because it allows for it to grow into each other and then contract away from each other. And so there's these little gaps like that to accommodate for the fact that things expand and contract.
Why have teeth?
Just to make it, I guess, harder for something to fall through there. I don't know.
Yeah, it makes sense. I mean, if it was flat, then
It's true.
It's just when I notice it has teeth. It's the way I've seen it. Okay. So let's do one example with that before we move to our next topic, which is where the chemistry comes in. So I'll do an example with this really quick. An aluminum cylinder 10 centimeters long with a cross-sectional area of 20 centimeters squared. All right, we're going to need to draw this picture. So we have an aluminum rod, and it's attached to two ends. Here's our rod. It's 10 centimeters long, and the cross-sectional area is 20 centimeters squared.
okay.
At 17.2 degrees Celsius, it just slips between the walls. Calculate the stress in the cylinder and the total force it exerts on each wall when it warms up to 22.3 degrees Celsius. So 17.2 and then 22.3. So 17.2, what was the other number I said? 22.3? 22.3. Okay. Okay. So here's two walls that are indestructible walls relative to this aluminum. It's aluminum, so we're going to need to look up its alpha and Young's modulus for aluminum.
Is there a table for Young's modulus for?
Yeah, that's clear back in like chapter 11. So
Yeah.
have fun with that.
Um,
Anyways, so we'll need to look up what those values are for aluminum, but we know what they are.
okay.
Right?
Mm-hmm.
So here's a physical scenario. I actually have this little strip that's 10 centimeters long. So right now we're in this room, and the temperature in this room is 17.2 degrees Celsius. I take an aluminum rod and I stick it between two walls in our room, which are only 10 centimeters apart for some reason, and it perfectly slides in there.
Okay.
Then I go over to the thermostat, I jump up the temperature to 22.3 degrees Celsius. And so now that rod's going to expand.
Yes.
Or it's going to try to expand, but it can't, because the walls are holding it in place. So our job is to calculate
The stress?
calculate the stress in the cylinder and the total force it exerts on each wall when it warms up. So we're looking for the stress, and then we're looking for the force.
Well, we know the area, so that's pretty easy.
So first we calculate the stress from alpha times Young's modulus times our change of temperature. And so, since it's an example problem, I should be able to see the alpha he used. Okay, Young's modulus for aluminum is 7 times 10 to the 10 pascals. 7 times 10 to the 10 pascals. And our alpha for aluminum is 2.4 times 10 to negative 5. And we didn't really talk about the units on alpha, but it's going to be 1 over Kelvin, or 1 over Celsius. We typically use Kelvin, but Celsius and Kelvin count by the same units.
Why 1 over Kelvin or 1 over Celsius?
Yeah, let's look at the units here. Over here we have meters. Over here we have meters. Over here we have Kelvin. And so this has to be 1 over Kelvin. So when we multiply it out, we get meters. Okay, so there's our alpha, there's our Young's modulus. So now we can calculate the stress on the system. And so we take 2.4 times 10 to the negative 5 times 7 times 10 to the 10 times our change in temperature. Okay, we didn't calculate that, but our change in temperature is 22.3 minus 17.2. Even though these are Celsius and we typically want it in Kelvin, Celsius, the change in temperature is going to be the same whether it's in Kelvin or Celsius. So we don't need to convert it. We could have, but we would have gotten the same thing. So 8.6, okay, 2 significant figures, yeah. So when we calculate this, this comes out, F over A then, well this value here comes out roughly, I already forgot, 8.6 times 10 to the 6, negative, I didn't put the negative sign in there, negative 8.6 times 10 to the 6, and I guess we'll call it, say, newtons per meter squared. Pascal, duh. Pressure, force over area, pascals, same thing.
Oh, pressure is just stress?
Yes, force over area, pressure, stress.
Okay.
Okay, so there is the internal, there's the thermal stress inside of our system, right? And then we were to calculate the force. Okay, so to get the force now, we just multiply our pressure by our area. Now remember, we need to convert 20 centimeters squared to meters squared.
Which is just 0.2 meters.
0.0. No,
Right?
he's right.
Okay.
You positive he's right?
Absolutely positive. Like a proton.
So we're going to take that and we are going to multiply it by our area. And you said our area is what?
0.2.
0.02?
0.2.
You guys, how can I make this quick once and for all so we don't have to say it again?
Okay.
If I, let's see, we'll just do it in force. Well, that's not really a unit. What's the best way to say this? Okay, we can still do this. 20, let's say that this is 1 meter by 1 meter.
Okay.
Okay? So this right here, if we divide this up into tenths, so kind of hard to do. There's tenths. Maybe an easier way to do it is just convert the units rather than drawing a picture. Okay, let's do it the long way. If you have 20 centimeters squared, then we can multiply that by how many centimeters to 1 meter?
100.
100. So we multiply it by 1 meter over 100 centimeters.
Yes.
And then we need to multiply that by 1 meter over 100 centimeters.
Again?
Yes, because you need to do both of them.
Why would you want to do both?
Centimeters squared.
Because it's
You signed
centimeters
up with
squared.
meters squared.
We want meters squared. An area is meters squared.
Isn't there 100 centimeters squared and 1 meter squared?
Huh?
No, there's not.
No, there's not.
Yeah, I see it now.
Which is the point. So I was trying to draw it with our figure. So I'll try and draw our figure again. And if we divide this up into tenths. Okay, each one of these tenths is 10 centimeters. Right?
Okay.
Yes.
So this right here is 10 centimeters by 100 centimeters. This is 200 centimeters squared. Here's a square meter. Here's 200, or not 200, sorry.
Yeah.
Here's 1,000 centimeters squared.
Okay.
That's way less than 0.2 meters squared. 0.2 is this. 1/5 is that.
Yeah, but isn't that
1,000 centimeters squared is that. 20 centimeters squared is absurdly small.
Yes.
It is nowhere 1/5 of a meter. Of a square meter. That's the intuition I'm trying to get you to see. I mean, this is less than 5 centimeters by 5 centimeters. 5 centimeters by 5 centimeters. Compared to 2/5 a square meter. I mean, I know this is just a yardstick, not a meter stick. But 2/5 a square meter, that's like take, or 1/5 a square meter, take 1/5 down, and then 1/5 all the way across. It's a way bigger area. I don't know how to get you guys to, your intuition check to instantly check that, and to see how insane it is to say something like 20 centimeters squared is anywhere near 1/5 a meter. Like, that's crazy talk. Anywhere near 1/5 a square meter, I mean.
Yeah, square meter.
Yeah. So when we're converting to square meters, it definitely can't be 0.2. Your brain should throw that out. Whoa, that's not even close to right. And if you're worried that you're going to get confused, converting to units the nice slow way will never steer you wrong.
Okay.
So when we divide by 100, and then divide by 100, basically we need to shift our decimal place 4 units that way. So 1, 2, 3, 4, so it's going to be 0.002 in terms of meters.
Now that's 10.
So this is equal to F over 0.002 meters squared. 0.02 meters squared.
No, because you shifted it 4.
Oh, 0.002, thank you. I had it right the first time. Right?
Yeah.
Okay. So now, when we're calculating our force then, we're going to multiply by the area, which is going to make it much smaller. And we should get, to choose significant figure, 17,000 newtons. Negative 1.7 times 10 to the 4 newtons. So So F comes out approximately negative 1.7 times 10 to the 4, or 17,000 newtons. And that's the force on the wall. And it makes sense that it's negative, right? Because it's pulling against the wall. It's not, wait, no, it's pushing into the wall.
It's pushing against the wall, yes.
That's the force that the wall exerts on it. If we call that way positive, the wall's pushing it that way.
Which is stress. That makes sense.
Yeah, the force that is being pushed onto the system to keep it this way. So the system wants to expand that way. There's a force that way of this much from the wall holding it in place. Okay, that makes sense.
Why doesn't it want to expand to the left?
Well, it does. You got the same problem. It wants to expand that way. The force won't let it, and the force is opposing the way it's trying to move.
Okay.
Okay. So that's that. So now quantity of heat. Okay. Temperature versus heat. Should we do that one first, or try and understand heat as energy? Let's start with temperature versus heat. Okay. Heat, I'm not going to get around this. Heat and energy are the same thing. So heat is a transfer of energy.
Yeah.
Okay. So heat is a transfer of energy. That's how I'll refer to heat. Now, what's the difference between heat and temperature? Temperature has to do with the state of the actual system. Heat has to do with how temperature is changing. So let's try and give you an example really quick. You come into this room and you fill the plastic table, and then you fill this metal piece right here. Question, which one's colder? Is the table colder or this colder? Or fill the wood desk, which is colder? So you can fill the wood desk, you can fill your plastic table, come fill this metal. Which one's colder and which one's hotter?
The metal's colder.
The metal be colder.
And the plastic's hotter.
And the plastic's hotter? And what about the wood desk? Do you think it's hotter or colder than the plastic?
Colder than the plastic.
So we know that it's roughly 70 degrees in here. What would you guess the temperature of each of these things are? Just completely roughly.
70.
Like 68, I'd be like.
So if the air right here is 70, you can kind of feel the air. Wiggle your hand around.
Okay.
So if the air is 70, then the desk, those tables you say are like 68.
Yeah.
You want to come fill the metal? Feel free to fill the metal if you want.
I'm sure it'll be like
54.
54, 60.
I'd say 64.
Okay. Now, here's the truth. Everything in this room is roughly the exact same temperature. And there's not a big difference in temperature between this metal, between this, between the air, and between that. They're all roughly the same temperature. Yet, it feels a lot colder when you touch this metal.
Yes.
Because what you feel is not temperature. Your body doesn't have a way of feeling temperature. Instead, what you're feeling is heat leaving your hand. Heat is going out of your hand into the table, into the metal. And since the heat isn't able to flow through metal quite readily, metal's a pretty good conductor of heat, the heat flows pretty fast. And so it feels colder to you, because heat is leaving you at a faster rate than when you touch this table, than when you touch the wood, than when you touch the air. So air is not a very good conductor of heat. Metal is a wonderful conductor of heat. And you already have great intuition for this. There's a pot on the stove, and you stick your finger an inch away from the stove, that doesn't burn so bad, because that little inch of air can't really conduct the heat. You touch the stove now, you touch the metal pot, and suddenly it burns, because metal is a great conductor of heat. And it gets that heat into you really quick.
Yeah.
So everything in here, roughly the same temperature. So they're all basically the same temperature, but the heat that you feel, the heat that you put into the material is very different depending on which one you touch. So heat is the transfer of energy.
Transfer of energy.
Transfer of energy.
Okay.
I am heating up this piece of metal. more heat is leaving me and going into that metal faster than if I were to touch the desk, for example. And eventually, if I touch this long enough, then me and that piece of metal will come into thermal equilibrium. And my body temperature is 98 degrees. This metal piece is roughly 70 degrees, 72 degrees, whatever it is there. If I touch it long enough, eventually we'll come into thermal equilibrium. Because my body keeps on producing more and more heat. It's one of the amazing things our bodies are able to do. And so eventually I'd make the metal right here the same temperature as my hand.
And your hand isn't necessarily 98 degrees.
My hand isn't necessarily 98 degrees. Because your hands, your extremities are typically a little bit colder than the main part of your body. Because they get heated up through blood pumping through you.
Yes.
One of the ways. Anyways, so that's the difference between temperature and heat. I can't talk about the temperature going into the table. That doesn't make sense. It's heat going into the table as I touch it.
But the temperature is going up.
The temperature goes up as a result of heat going into it. But it's bad to say I put 2 degrees Celsius into this table. That doesn't make sense. I put so much heat into this table that it raised the temperature of the table by 2 degrees Celsius. That makes sense.
Okay, I see the difference.
Okay, so heat versus temperature. Heat is energy in transition.
Yes.
Okay. Now, let's talk a little bit about, well, maybe we can read exactly what they say. The interaction that causes these temperatures to change is fundamentally a transfer of energy from one substance to another. Energy transfer that takes place solely because of temperature differences is called heat flow, or heat transfer. And energy transferred in this way is called heat. Okay. So that's exactly what heat is. Make sense?
Yeah, that makes sense.
That's a fair way to put it. Okay. So now let's talk about a measure of energy called a calorie. You've heard about a calorie before. What is a calorie? A calorie is 4.186 joules. So 1 calorie is equal to and I already forgot what I said. 4.186. 4.186 joules.
Don't you consume calories?
Don't you consume calories? Yes, you do.
So you just
Now,
consume joules?
Yeah. Calories are energy. Joules are energy. You get energy from food by consuming calories.
Oh, yeah.
That's how you get your energy. I eat the food, which has calories in it, and I convert that potential energy in the food into kinetic energy when I start walking.
Okay.
As one example. So, but this isn't the calorie that you eat. So 1 calorie is 4.186 joules. Then we have a notion of a kilocalorie. A kilocalorie, lowercase c, this is a lowercase c, which we also sometimes represent as a calorie with a capital C, which is equal to 1,000 calories, which is equal to 4,186 joules. And that is a calorie that's on food. So when you look at a wrapper and it says this has 86 calories, you'll notice it's a calorie with capital C. And calorie with capital C is shorthand for 1,000 of these calories. So when you consume 1 calorie in your food, you consume 4,186 joules of potential energy.
That's a lot of energy, isn't it?
I don't know what a lot is versus a little. A lot and a little are qualitative terms. Now, I can't remember exactly how we define a calorie. It's the amount of heat you can get from something. It's right here. The calorie is defined as the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. So how much heat does it take to raise 1 gram of water by 1 degree Celsius? 4.186 joules. 1 calorie with the lowercase c.
Oh, I see. Okay.
So that's by definition what a calorie is. And it's actually technically what it takes to raise water from 14.5 degrees. That technicality doesn't matter. It'll just confuse you. 1 degree Celsius. Let's leave it at that. Okay, so that's what 1 calorie is defined to be. And so we define it in terms of how much heat it could potentially produce.
Yes.
And of course, you're utilizing the fact that you can get heat from calories all the time. That heat is just a different type of energy. Just like a calorie is potential energy, you convert it to heat.
Yeah,
That's happening in your body all the time as your body heats itself up. You also notice this all the time with a log, for example. When you burn a log, it had a bunch of potential energy in there, a bunch of calories in there. As you burn it, you release that energy. Had a bunch of potential energy, you release that. Or if you were to go get a tortilla chip, you'd also notice you could take a lighter to a tortilla chip. It would act as a fuel source.
Yeah.
It's because you're literally burning the calories. And so that's what it means to burn calories. You actually burn the calories. And you do the same thing inside your body when you burn calories. The chemistry that goes on your body to burn up a carbon chain is not that different from the chemistry that goes on when you burn when you burn a log. Pretty similar.
Basically the same principles.
It's basically the same thing. Yep. It's basically combustion. You basically combust your food.
But you... Never mind.
That's why you got to breathe in that oxygen and you breathe out carbon dioxide and water. And you ate the carbon chains earlier. So you start out by eating the carbon chains,
Yes.
and then you breathe in the oxygen. And so you have a bunch of carbon, hydrogen, and oxygen in you, and you release the carbon, hydrogen, and oxygen. You take it in as carbon chains and oxygen gas, and you breathe it out as carbon dioxide and water.
That's pretty cool.
So, same thing the log gives off as you burn it. It gives off carbon dioxide and water.
Okay.
Strange as that is. You burn a log and it gives off water.
Is that what smoke is?
Smoke is a lot of stuff. It's a lot of just debris from the actual stuff there.
But water is part of that?
But water is in it.
What the heck?
Water is one of the byproducts of burning a log.
Cool.
Anyways, so yeah, that's what's going on in your body. You're burning it. And so, probably worth noting, the physicist's diet plan. What's your diet plan if you're a physicist? If you want to lose weight, how do you lose weight?
You don't eat.
It's pretty simple. Consume less calories than your body uses, and you're guaranteed to lose weight. How do I know? Conservation of energy.
Yep.
You can't cheat the system. All the energy that goes into your body goes into your body through food. So we can measure how much heat you give off in a day. That's energy. How much you move around. There's work going on inside your body, like pumping your blood, and it loses some stuff to friction. Again, that would all come off as heat. So all your internal stuff you can pretty much capture as coming off as heat. So if we measure how much heat is coming off of you, and on top of that we measure how much you physically move around, how much work you do, we could get a good feel for how many calories you burn a day. And then if you don't consume more calories than you burn a day, you'll lose weight. It's impossible not to. Because the energy has to come from somewhere.
So it's really straightforward.
It's really straightforward in the sense of if you just want to lose weight. Now you got to worry about other things because biology's messy. So there are certain vitamins that you need to take in every day, for example. I don't know, you need them on a daily basis. And you can't just eat a diet of pure calories to stay alive.
Why not? Because of those vitamins?
There are certain vitamins that you need. There's proteins that you need. You need to make sure you're getting protein. So if you just consume something that doesn't have protein, you could die eventually. What's the disease that all the sailors get?
Scurvy.
Scurvy because of a lack of
Citrus.
vitamin C. I think it's vitamin C.
Yeah.
Vitamin C. So their diet, so a lot of your vitamin C came from foods that basically didn't preserve well. And so a lot of sailors would get scurvy because they didn't have enough vitamin C.
What is scurvy?
Doesn't matter. Some disease that you get from a lack of a vitamin. So there's basic things that you need to make sure you have in your diet, but once you check off your checklist of I need these basic things and I need this many calories, just make sure in checking off that list you don't consume more calories than you burn, you'll lose weight. And you could probably do it pretty simply. I would guess that dogs pretty much eat everything you eat. You could probably just go measure out dog food and be fine. I would guess. I'm sure there's probably something similar.
Yeah.
I don't know what it is. You need to find out what it is. Some human food. Same way you can just go buy a big bag of dog food that has everything your dog needs. Go buy a big bag of human food.
Protein shake.
I doubt that would have everything. It would have your protein, but does it have everything? I don't know. Anyways. So heat. We're talking about heat. And we talked about calorie. By definition, a calorie was how much heat was required to raise 1 gram of water 1 degree Celsius. Right?
Yes.
So in general, our equation is the amount of heat required to get a particular temperature change in something. We use Q for heat. The amount of heat we need to get the temperature change in something depends on how much of that something there is. So for example, if it takes me 1 calorie to raise 1 gram of water 1 degree Celsius, how many calories does it take to raise 2 grams of water 1 degree Celsius? 2 calories. And so if you double the amount of mass, then you double the amount of heat you need to get the same temperature change. And then finally some constant. C. C is called the specific heat. Specific heat. So C, this is a constant that depends on the material you're talking about. The specific heat of water is very different from the specific heat of aluminum. Aluminum is going to have a low specific heat. It's real easy to heat up aluminum. Water has a very high specific heat. One of those other interesting properties about water is it has a very high specific heat compared to other elements, or not elements, but other materials.
Well, what about something like steel?
Steel has a very low specific heat. It is very easy to heat up steel.
Oh.
It is very hard to heat up water. High specific heat means Q has to be big to make these change, because this is already big.
Yeah, that makes sense.
So water has a high specific heat. It's hard to heat up water. Water can absorb a lot of heat, which I'm not sure if that's why we use water in putting out fires. That's my guess.
Well, also because it smothers out the oxygen.
Yeah, that's the other thing I was thinking is a filament of water could cut off the thing's burning's access to oxygen. But I would guess that this has a huge part to do with it. Water can absorb a ton of heat.
What about stuff like dirt?
Dirt heats up easier than water does. The majority of things around you heat up faster than water does. And so water is a great coolant. And so there are specific things designed to have a higher heat, higher specific heat than water. And so a coolant in your car engine has a higher one than water. But water was used as a coolant for a long time. Because it has such a high specific heat, it can absorb a lot of heat without making a huge temperature difference.
When did it start boiling though?
Eventually, but it takes a ton of energy to get water boiling.
Interesting.
Relative to other things. So, that's our specific heat. Let's see. I think there was something else I was going to say before we moved on. Specific heat, talking about water. Water can absorb a lot of heat. There were some daily experiments I was going to point out to you. That makes this fact clear. Oh no, I'm just going to point out something interesting.
Okay.
So the fact that water can absorb a lot of heat, this isn't actually as related to that as I was thinking at first, but just a cool experiment did once. And one you can try yourself. I don't know, Masada still use little paper cups.
Probably.
Yeah.
So you can go get one of those little paper cups from Masada, go get a little Bunsen burner from the lab, and then put just like put like a centimeter of water inside that cup. And then go put the cup above the Bunsen burner. And what do you think is going to happen?
The cup's gonna light on fire.
The Bunsen burner is going to burn a hole through the bottom of the cup and the water is going to pour out, right?
Yeah, that makes sense.
That makes sense? That's not what's going to happen.
Well, what's gonna happen?
That cup is not going to burn until all the water is boiled out of that cup. And the amount of time it takes to boil that water out of that cup is insane.
Is that because it'll just seep to the bottom?
The heat, so the bottom of the cup is there. Here's a little bit of water inside the cup. You heat up the paper out of the cup, but then the water heats up, taking the heat out of the paper. And so as you add heat to the paper adds heat to the water, and so the water heats up. And water can't get very hot. It can only get 100 degrees Celsius before it starts boiling.
Yes.
We'll talk about this more next time, but water can only get 100 degrees Celsius before it stops burning. And so the bottom of the cup can't really get that hot. Because it's transferring the heat to the water.
So all of it will have to evaporate out before.
Almost all of it will have to boil out. I mean, there might still be like a little bits of water there, I don't know. Before you burn a hole in the cup.
Interesting.
It's going to take a long time to burn a hole through that cup. So there's a simple one you can go do.
That's cool.
Anyways, back to this equation right here. So if we just have an infinitesimal change in temperature, that produces just an infinitesimal change in heat, or vice versa. If I do add a very small amount of heat, delta Q, dQ, then that's going to create a comparatively small change in temperature, dt.
Yes.
And then, so if we solve this for heat, the specific heat C is equal to 1 over m times dq dt. dq dt being our change in temperature, or our change in heat with respect to temperature. So they also give you that equation. So continuing with this equation for a second, let's see, what do they call capital M here? So I'm going to erase that. That's a useful side equation, but maybe come back and start using space over here. So rewriting this equation again, we have Q is equal to specific heat times mass times delta T, right?
Okay.
But another way that we can represent mass is we can represent mass as, we can represent it as N, the number of atoms that there are, times M, the mass of each of those atoms.
So the atomic weight, basically.
Yes. I'm assuming N there is the number of atoms, not the number of moles. Trying to see where they name it specifically. Okay, so they are, so never mind. N, rather than being the number of atoms, and M, the mass of the atoms, instead N is the number of moles, and it's still the atomic mass, but rather than it being the actual mass of one atom, it's the amount of grams per mole. It's grams per mole.
Okay.
Why grams and not kilograms?
Because that's how we defined a mole. I don't know why. But a mole was defined so that 1 mole of hydrogen is equal to 1 mole of hydrogen is 1 gram, not 1 kilogram.
So are we gonna need to be?
You're gonna have to convert this all the time from grams to kilograms. Yep. So M there, that's your molar mass. Again, you get that from just a periodic table,
Yeah.
and we call it the molar mass. The molar mass is in grams per mole. It is not in kilograms per mole. So have to be aware of that. But it's a really easy conversion to do, right? For example, what's one that we already did? Oxygen. What was our atomic weight of oxygen? 16. So if 1 mole of oxygen weighs 16 grams, then how many kilograms does it weigh?
0.016.
Yeah.
Yeah, just 16 times 10 to the minus 3 kilograms. So really easy conversion to do. I recommend always and forever just doing that conversion. And always working with it in terms of kilograms.
Okay.
Okay. So the product MC we call the molar heat capacity. So when you look up on a table, then they also for each atom, because notice that N, oops, let me change the order of these, or I'll just rewrite it right here again. This is lowercase e, by the way, lowercase e times N times delta T. Okay, so notice that your C here, your specific heat, this depends on what type of material you're talking about,
Yes.
right?
Mm-hmm.
Specific heat of water is different from the specific heat of helium. Your mass here, your molar mass, depends on what you're talking about. The molar mass of water was 18. The molar mass of helium was 4. So since both these two constants together depend upon what you're talking about, we can combine those two constants into a new constant, which we call capital C, which is your molar specific heat. So times N times delta T is another equation, where that capital C is just little c times big M. Okay, and now phase changes. Still got a bit to go here. So now I'm going to plot a system, and I'm going to plot temperature versus, on here I'm going to draw how much energy I put into the system.
Okay.
Now as a general rule, if you put energy into the system or heat into the system, maybe Q, specifically say the heat we put into the system, in general temperature goes up, right?
Yeah, that makes sense.
And so I'm going to start out with an ice cube. I'm going to go get an ice cube out from Antarctica, and I'm going to start adding heat to that ice cube. You with me?
Mm-hmm.
Now, I don't know what the temperature is in Antarctica, but we'll pretend that this thing starts out at like, I don't know, negative, we'll say that this is on a Celsius scale. So we'll say it's at negative, I don't know, 30 degrees Celsius. Who knows? Here's where it starts out. Our ice cube, right?
Yeah.
And I start adding heat. As I add heat to the ice cube, it's going to heat up and heat up and heat up and heat up and heat up until it reaches 0 degrees Celsius, freezing point of water.
Okay.
Now, when I have an ice cube here, and I now got it at 0 degrees Celsius, we know that that's the melting point for ice. The melting point and the freezing point are the same point.
Yes.
Melting point and freezing point for water / ice is 0 degrees Celsius. Now, it's not like if I go get an ice cube from Antarctica, and I slowly heat it up, get it to the point where it's at 0 degrees Celsius. It's not like if I add 1 more calorie, suddenly all the ice turns to water.
No, it's...
It just starts to melt.
Mm-hmm.
And so now, as I add heat, the temperature doesn't change and the ice just melts. And the temperature stays the same until all the ice melts. And then, once all the ice is converted to water as I add heat, the water starts to heat up. And now it's not like once you get water to boiling point, suddenly all the water turns to steam. Once I got the water to boiling point, so this is, cut it down lower, so let me have it here. So I get it up to 100 degrees Celsius, the boiling point of water. Once I get water that high, it just starts converting the water to steam. And we'll have to keep adding heat until all the water is converted to steam. And it's not until all the water is converted to steam that I can start raising the temperature again of the steam.
Yes.
And so that's called a phase change. A phase change is where it goes from a gas to a liquid, or where it goes from a liquid, or it goes from a solid to a liquid, or a liquid to a gas. Here it was a solid, here it was a liquid, here it was a gas.
Yeah.
And it takes a lot of energy, not only to heat it up, but then to convert it. And so, it's technically not impossible, but I'm going to say it's impossible, so I'm going to lie to you. It's mostly true.
Okay.
It's impossible for water to exist below freezing points. And it's impossible for ice to exist above freezing points. And so when you get your cold drink of ice, right, and you put ice cubes in there, and it gets it cold, putting in more ice cubes doesn't change anything. It just helps keep it cold longer. You can only get water this cold. You can't get it any colder. Once you get your water this cold, adding more ice cubes to your drink isn't making it any colder. You're just helping it stay colder longer. What were you going to say?
I was saying, isn't there a point for water where it's in equilibrium with all three states?
Yeah, we'll ignore that for a second, because you have to talk about different pressures, bring pressure into the equation there. So, talk about water here close to the surface of the earth. And this is the kind of experience you have in the kitchen. And so once you get your water up to boiling point, for example, you can't get any hotter than that. It's not possible. So once you got your water boiling, that's as hot as your water is going to get. It doesn't matter if you let the water sit there and boil for an hour. It didn't get the water any hotter. All you did was converted more water to steam.
Okay.
Does that make sense?
Not the ice one.
Not the ice one?
Doesn't like having more surface area of ice let the cold get out more?
So you put ice cubes in your drink. First, they're lowering the temperature of your drink.
Yeah.
And yes, the more surface area your ice has, the faster your ice cube will melt, the faster it will lower the temperature of your overall drink. Once your drink reaches 0 degrees Celsius, you can't get it any colder. And still have it be a drink.
Oh yeah.
In other words, if I've got a cold drink and it's already this cold, and I go and I stick it in the freezer for 10 minutes, and then go pull it out, it didn't get any colder, it just got a thin amount of ice on it. It just converted some of the water to ice. The water isn't any colder. The ice can be colder now, but the water is still just 0 degrees Celsius. You can't get it any colder.
Okay.
Mm-hmm.
This is the coldest water can get, this is the hottest water can get. Outside of that, you start to go through a phase change. And so, we can calculate the amount of energy that it takes to go from here to here. That's given to us by these equations we've been using. You can use this, you can use this, you can use this, you can use this.
Where's the energy in that?
Q is the energy.
Heat is energy, yeah.
Oh, heat, yeah. Sorry. Heat or energy. I'm going to interchange those all the time. I'll try to remember to say heat. Heat. The amount of heat you need to get a certain temperature change, so to go from negative 30 to 0, is right here. You look up the specific heat of ice, the mass of the ice that you're talking about, and the temperature for that. You go calculate it, that's the energy you need to go from here to here. If we want to go from here to here, we use this equation again. We go get the specific heat for water, the mass of water that we're talking about, and the temperature change we want is 100 degrees. And we can calculate the heat that's required to go from here to here.
Yeah.
And similarly, to go from here to wherever our final temperature is when we end our experiment, however high that is, we'll pretend that's 130 degrees Celsius. Again, you can use that equation to calculate the heat that you need to go from here to here. So this equation helps us calculate the heat in this part, and in this part. What about the heat here and the heat here?
And there's no
It
change in
just-
temperature, so.
There's no change in temperature, but you still need to add heat to the system.
Mhm.
So
And it takes
volume-
a ton of heat. It takes way more energy to think about how much energy it takes to get water boiling. Right? You leave it on to stall for 10 minutes, okay, your water's boiling. How long would you have to leave it there boiling to convert all the water to steam?
a long time.
A really long time.
Yeah.
So this energy compared to this energy, I drew it short. But for water, no, it's not even comparable. This is way more than this.
Yeah, that makes sense.
Right? So it still takes a lot of energy. And so how much energy would it take? How would we make this calculation? How would I calculate how much energy it takes to convert all my water to steam? Or to convert, for these parts, or to convert all my ice to water. How much energy does that part take? And so that's the last equation that we need.
Wouldn't that just be in direct correlation with volume? So if less
With
the
mass.
volume,
And so for that one, it's Q is equal to some constant, plus or minus some constant, L I think they use, times and the mass you have. Plus or minus depending on, you need to add the energy if we're converting water to steam. You need to subtract the energy if you're converting steam to water.
that makes sense.
So plus, if we're talking about adding energy going this way, so our system's doing this, minus if we're talking about taking energy out of the system. Which you can take energy out of the system. How do you take energy out of the system? You watched it happen today in class. I touched the metal. Energy was leaving me. I'm getting colder as this is getting warmer. I lose energy, it gains energy.
Okay.
So you can pump energy out of the system, and we'll learn about how refrigerators work. That's essentially what they do. They pump energy out of your fridge to the external part of your fridge.
That's cool.
Okay. So L there is going to just be some constant that you have to look up on a table depending on your material. And then M is the mass of your material. And this constant is often referred to as the heat of fusion, is the name of that constant. And so you'll have a table for that as well. And so table 17.4 in your book, it will give you the melting point of a bunch of different materials. It will give you the boiling point of a bunch of different materials. Notice that this temperature was a melting temperature. And then this temperature is the boiling temperature.
Yes.
So melting point and boiling point, those are the only two we care about. We're only going to talk about going from solids to liquids or liquids to gases. We're not going to talk anything about plasma or Bose-Einstein condensate because they don't fit into this simple picture.
Okay.
So we'll only be talking about those three states of matters, and so we'll only be talking about those two transition points, this transition point and this transition point. Now there is also possible the case, some materials, it's impossible for them to exist at a liquid state.
Mm-hmm.
They go directly from a solid to a gas.
What sort of materials do that again?
You're very familiar with one.
Solid to gas.
It goes from solid to gas. Sometimes you use it to cool down drinks. Gives off a lot of gas as it cools down the drink. Often used at Halloween time.
Oh, yeah.
Like dry ice?
Dry ice. What is it, dry ice?
It's carbon dioxide?
It's just carbon dioxide. It's frozen carbon dioxide.
That's right.
And so it goes directly from heat to gas. And going from heat to gas takes a lot of energy.
Yes.
And so it sucks up a lot of energy out of whatever system it is, which cools the system down really fast. So dry ice is great for cooling down a system.
Yeah, it is. It's pretty cool.
So that's why dry ice works so well for freezing things, and why you got to be careful not to just go grab a thing of dry ice.
It'll just zap all your energy.
It will suck the energy out of you. Yeah. It'll be very cold. So you're
Sure.
more careful with dry ice, right?
Yeah, I had to wear gloves when I played with it.
Right. Anyways, so that was that.
Does it do any harm other than just making it really, really cold?
Just cooling it. That's what it does. Making it really cold really fast.
Yeah.
Yes. Okay. Mechanics of heat transfer. Okay. So now, roughly 3 different ways that we can transfer heat. So, one way that we can transfer heat is if I have a long metal rod and I heat up this end of the metal rod and Jeremy's holding the other end of the metal rod, eventually he'll feel some of the heat.
Yeah.
Right? And if the metal rod is short, he'll feel it really fast. If the metal rod is long, it takes longer for him to feel the heat and he won't get burned as much. Right?
Okay.
Mm-hmm.
So, that kind of heat, where the heat is conducted through the material, we call conduction. And the amount of heat that is transferred, the heat transfer rate, the amount of heat per time, so we use H for the change in heat with respect to time. Notice that's time, that's not temperature. So before, I don't know what I had for you, I had something like C is equal to 1 over M dq dt. That was a temperature, capital T. This is a change in heat with respect to time. How much heat per second can I get to Jeremy? And the
What
amount
is
of
it called again? What is H called?
heat current.
Heat current. Okay.
Heat current. I'll just call it change in heat with respect to time, or the derivative of heat. Anyways, so when we're conducting it through a material, what adds to Jeremy feeling the change in temperature quicker, and what detracts from it? So if Jeremy's holding a metal rod, let's think for a second. The longer the rod is, the less heat Jeremy feels, right?
Yes.
Mm-hmm.
So the longer the rod is, the less heat Jeremy feels. So L needs to be down here in the denominator.
Okay, that makes sense.
If the rod is thicker, does he feel more heat? Or if it's thinner, does he feel more heat?
Thinner, I would assume.
Do you mean for how fast it goes?
Imagine that the rod is really short now, right?
Okay.
But the size of a plate.
The size of a what?
A plate. A plate.
Oh, a plate.
So we've got a really big area, really skinny rod. I superheat this side, and I shove this side against Jeremy.
Oh, he's gonna, yeah.
Is he going to feel a lot more heat than if that thing were the size of a needle? And the needle were touching Jeremy?
Yeah, that makes sense.
So the greater the cross-sectional area, the more heat transfers.
Okay.
So we expect to see area up there. Obviously, we expect a constant, depending on the material. Okay. And then finally, this last one, let's see, heat of, what's the H for though? Sorry, just trying to think about what these subscripts are for, which is which. I'll write it up here and then find out where the subscripts are coming from. TH minus TC. The difference in temperature. So TH is the temperature where I am. TC is the temperature where Jeremy is.
Okay.
If it's already the same temperature between me and Jeremy, no heat transfers through the wire.
Yes.
It's all zero.
That's all zero.
Oh, I see.
If there's a huge temperature difference, then a lot of heat transfers. If there's a small temperature difference, only a little bit of heat transfers.
Okay.
Make sense?
Yeah.
And then I was going to try and find why they did sub H and sub T. Maybe they're just thinking hotter and colder. Your hotter source to your colder source. Because the heat flows from the hotter source to the colder source. You never have heat flow in the opposite direction. It'd be really weird if I came and touched this thing and it started heating me up rather than me heating it up.
Yeah.
Right? Heat always flows from hot to cold, not from cold to hot. Make sense?
Mm-hmm.
Okay. that was one way heat is transferred, through conduction. Another way heat is transferred, and we won't be able to capture this in the equation because it's way too complex, but is through convection. Convection. Heat is transferred through convection, which is when the heated up materials themselves move. And so convection is like air movement. If I want to cool down this room, what's one way I could do it? If this room were really hot, I could open all the windows and doors and let cool air actually flow in and hot air flow out.
Yeah.
Convection.
Okay.
Convection, you feel convection all the time. That's why you standing in front of a fan feels good. The air directly around you heats up because it's in contact with your body. And so your body is in contact with hotter air than the rest of the air in the room. When I blow you with a fan, the air that was touching you gets moved away, and so new cooler air comes into contact with you. And it can absorb heat.
Oh.
And as you blow that air away, new air can come into contact with you, which is cooler, which can absorb heat.
Yeah.
So you basically have like this little cushion of heated up air around you, and getting that cushion away helps you cool down some more again. And so that's why breezes help you cool down. Or why even if your eyes were closed, if someone stuck their hand really close to you, you'd probably feel the heat. Because you're capturing that cushion of air between the two of you more thoroughly.
Yeah, that makes sense.
Okay, so that one's convection, and we can't get equations for convection because it's a mess of what's going on. It's just a bunch of jumbled up air particles moving around. And then the last one, the last way that we transfer heat is through radiation. Your body actually just gives off electromagnetic radiation on the infrared spectrum, heat. So if I were to look at you using what we often call heat vision goggles or infrared goggles,
Yeah.
then I would see you glowing. That's your body giving off a bunch of heat. Internally, a bunch of stuff is going on inside of you, and all those processes ultimately produce heat,
And they just
which is
jump
then
out of you.
sent off. Huh?
And that energy just goes out of you.
Yeah, electromagnetic radiation in the spectrum of infrared is just coming off of you all the time. And you're just radiating heat all the time. And that's not heat transferring through some medium. If I were to go stick you out in space, you still radiate heat. It's not just heating up the air next to you.
Okay.
Right?
Mm-hmm.
And so the equation for that one, it's not one that we're going to derive, it's one that you're just going to be given, is H is equal to A times E times T to the 4.
T to the 4.
Yes,
For radiation.
for radiation. This is the amount an object radiates. Everything in the universe radiates. This is the amount an object radiates at some given temperature. E here is not the constant number E that we know and love. E is a constant based on the material.
Okay.
So some materials radiate more than other. A is the surface area of the thing in question. The greater your surface area, the more heat you radiate.
That makes sense.
And so this is why, not why, but one of the reasons why, something like an elephant's heart beats way slower than a rodent's heart. Because a rodent has a ton of surface area compared to how much volume they have. And so they radiate off a lot of heat. And so they got to reheat their bodies a lot more. An elephant has a lot of mass compared to a little bit of surface area. Its surface area compared to its mass is almost nothing.
Yeah.
And so it doesn't need to produce near as much heat inside of it. And so typically bigger animals, their hearts don't beat as much because they don't need to conduct the heat through them near as fast. And they don't need to eat as frequently. Little rodents, they need to eat very frequently. I don't know how fast it is that they can starve to death, but it's a short period. It's like something like 8 hours.
Oh, wow.
It's something short like that.
But a whale can go days without.
But a whale can go forever. Right.
Yeah.
And part of that is how fast they need to restore it because they're losing heat so fast. So your greater your surface area, the more heat you radiate. And then the higher temperature you are, the more heat you radiate. And the higher temperature you are, also the higher frequency the heat is that you radiate. So this is just the energy of heat that comes off of you. But if we go back to our electromagnetic spectrum, and then it gets just super compact over there. You have gamma rays right here, right? And then you have X-rays right here. Then you have ultraviolet radiation. You have visible light. And then over here you have infrared, or what we loosely call heat. Infrared we also often call heat. So that's this wavelength. You're always radiating this wavelength of energy out into the universe. Sometimes when you heat up an object a ton, the heat that it radiates actually starts shifting into the visible light spectrum a little bit. And so you notice when you take a metal rod and you really heat that thing up and you raise that T a ton, then not only is it radiating just infrared, but it starts to radiate a teeny bit of red as well. And it starts to glow red.
Yeah.
Oh, that's pretty cool.
Right? And so our last equation that we need to put up here is just using this, but just in common sense way. The net heat that goes into and out of a system is going to be equal to oh my goodness, I can't believe I did that. Sorry, I missed a term in here.
Oh shit.
I missed our constant.
Isn't E your constant?
E depends on your material. Sigma is a constant. Sigma is the same for everyone. Sigma is the same for everyone. E depends on your material. So sigma is just 5.607 times 10 to the minus 8. So it's like G in Newton's equation.
Say that again.
Doesn't matter. 6.07 times 10 to the minus 8 is what sigma is. But it's a constant. So this is just a constant period. This depends on the material you're talking about.
Okay.
This is surface area, and then this is its temperature in Kelvin.
Yes.
So an object of 0 degrees Kelvin doesn't radiate at absolute 0. But nothing's at absolute 0, so everything radiates.
Supposedly, could you possibly get something to absolute 0?
No, not really.
Even if it was in the middle of space with nothing around it?
No, there isn't nothing in space. There's fluctuating fields everywhere in space. This idea of a perfect vacuum, according to our current physics, there's no such thing. And so you can get really, really close to absolute 0, but perfect absolute 0, no.
Okay.
Okay, and then so now, now we say that you're standing in this room, and we want to calculate how much energy is leaving your body.
Yes.
Now we don't use this equation, because while you're radiating out heat, heat is also being radiated into your body. You're heating up your environment, but your environment is also heating up you.
Okay.
And so we calculate the net change in heat is equal to how much you're radiating minus how much is being radiated into you, which is going to be T of your surroundings. T sub S for your surroundings. Or if we just factor out everything that's the same, then it's just going to be A E sigma times your temperature to the 4 minus the temperature of your surroundings to the 4.
Yeah, that makes sense.
Okay. And that finishes up the material. One more thing to mention back to this. So, one of the things we talked about is it takes a good amount of energy to convert water to steam, to make water go from its liquid form to its gas form, right? That's one of the reasons that sweating is so good at cooling you down. You put the water on the outside of your skin, that water evaporates. As it evaporates, it absorbs a bunch of heat, helps cool you down. Okay, so let's pick some example problems to do since we didn't do a lot of them.
Okay.
I don't even know where to go. Let's try to do one that's like the picture I have on the board. So let's see. A camper pours 0.3 kilograms of coffee initially in a pot at 70 degrees Celsius into a 0.12 kilogram aluminum cup initially at 20 degrees Celsius. What is the equilibrium temperature? Okay, so we've got our cup, we've got our hot coffee. I pour the coffee into the cup.
Yeah.
The coffee is going to heat up the cup, which is also going to cause the coffee to cool down. What's the equilibrium temperature going to be when the coffee stops heating up the cup and the cup stops cooling down the coffee, when they're the same temperature? What's that temperature going to be?
Okay.
You understand the question?
Yeah.
Okay. So, I don't know if this picture is going to help much anymore. I'll try and do one that is based on that picture a little bit, so maybe we'll just slide down and get the rest of our blackboard here. And I'll draw over here. Okay. So get our numbers again. Try and remember these numbers for me. 0.3 kilograms, 70 degrees Celsius. 0.12 kilograms, 20 degrees Celsius. All right, Jeremy.
0.3 kilograms, 70 Celsius.
All right, Peter.
I don't remember what it was.
Come on.
I was writing it down.
Oh, you weren't looking at me? I was telling him to memorize the first two, you did the next two.
Oh.
I thought you were looking at me as I pointed at you. 0.12, 20. 0.12 kilograms at 20 degrees Celsius. This was coffee, which is essentially water. And this one's aluminum.
Okay.
Okay, so conservation of energy. The amount, well, let's see. What's the right way to think about this? The net change in heat is going to be 0. So the amount of heat that goes into this is the amount of heat that this absorbs from this. So the amount of heat, let's talk about the heat where it's going. The amount of heat that goes into the cup is going to be using just what's on the camera. Let's rewrite it over here. We're going to be using Q is equal to MC delta T, right?
Oh, so just the first one?
Yeah. So the amount of heat that goes into the cup
Okay.
is going to be equal to the mass of the cup times C times the change in temperature, which is going to be the equilibrium temperature minus its initial temperature, which is 20 degrees Celsius. Right?
We're looking for the equilibrium temperature.
We're looking for that temperature T.
How'd you get equilibrium temperature?
We don't know what that is.
I mean, why are you using that?
That's going to be the total temperature change. The cup is going to go from 20 degrees Celsius up to its equilibrium temperature.
Okay.
And now the heat that goes into the water is going to be M times C times, it's going to start out, it ends at 70 degrees, but it drops to its equilibrium position of T. So this is the energy that goes out of the water, this is the energy that goes into the cup.
Okay.
And those have to be equal. The energy that leaves the water is the energy that goes into the cup.
Yeah.
So, combine those all into one equation now. So this is equal to mc T minus 20 degrees. Now, I was very sloppy. This is the heat capacity of aluminum. This is the heat capacity of water. Those are different C's.
The masses are the
And
same?
the masses are different. This is
Yeah.
the mass of the water. This is the mass of the aluminum. And this is C of the aluminum. Okay. You with me?
Yes.
Why are they equal to each other?
This is the amount of heat that leaves the water.
Yeah.
This is the amount of heat that goes into the cup.
Oh, yeah.
All the heat that leaves the water, we're assuming goes into the cup. We're not going to account for any radiation going out into the atmosphere or any water actually bouncing off.
Okay.
Because how does your coffee actually cool down? Why does coffee cool down?
It It's exposed to the environment.
How does that make it cool down?
The air comes in and
What's physically going on inside your coffee cup, because what helps a ton is just put a lid on your coffee. Putting a lid on your coffee. Keeps it warm. It helps a lot. So what's happening is you have water molecules jiggling around a lot. They're all jiggling around. And eventually, I guess we'll probably talk about this later, because we haven't talked about the fact that temperature is really just a measure of the amount of kinetic energy in the system. The hotter the air is, the more the atoms are vibrating.
yeah.
Okay, so the hotter the coffee is, the more the water is vibrating. Eventually, one of these water molecules gets enough of a kick. It gets two water molecules just happen to hit it just right, that thing kicks off into the air. That's steam. And so that happens over and over again. Your highest energy water molecules keep getting kicked off. The ones with the most energy keep getting kicked off, leaving the least energy ones behind. And so your coffee cools down. And just putting a lid on there, so that when that thing gets kicked off, it eventually gets knocked back down into your cup, helps keep your cup hot.
And because you're blowing on it, is that just for...
Blowing on it is now using convection. That's using the fact that the air molecules here are already close to as hot as the water there, and when you blow away those air molecules, more air comes in and absorbs heat. So using two different principles.
Okay.
So one's blowing away the air molecules, another one's actually capturing those water molecules so that they don't escape.
Interesting.
Okay, anyways. So now we take this and we just solve for T and we're done. Right?
Yeah, that's pretty straightforward.
So we get MWCW times 70 minus MWCW times T is equal to MACA times T minus 20 MACA. Move all my T's over here. Oh wait, let's move my T's over here and my constants over here. So writing this side of my equation first, I get T times the mass of my aluminum times the heat capacity of my aluminum plus the mass of my water times the heat capacity of my water is equal to, and then we moved our constants over here. Oh no, we moved our constants over here. So is equal to 70 times the mass of my water times the heat capacity of my water plus 20 times the mass of my aluminum times the heat capacity of my aluminum. I don't know why I did that M so small. It's like I say meters. And then finally, T is equal to just this divided by this. We know all those numbers, plug them all in, we'll get the T. Make sense?
Yeah, that's pretty straightforward.
Okay. I want to find one that does what this thing is saying, though.
A phase shift?
Yeah. A hot pot of mass 2 kilograms, including its copper lid, is at temperature 150 degrees Celsius. You pour 0.1 kilograms of cold water at that into the pot, then quickly replace the lid so no steam can escape. Find the final temperature of the pot and its contents, and determine the phase of the water, liquid, gas, or a mixture. Assume that no heat is lost to its surroundings. Okay, so this is a cooler one because I bet some of the water is going to turn to steam. So we're going to find the equilibrium temperature again, but this time the water might actually turn to steam, and so our equilibrium temperature for our water might actually be up here, and so a lot of the energy might have to go into converting that water to steam.
So how do you do that?
Let's figure it out. That's why I wanted to do one like this, to make sure you saw one.
Okay.
Okay, remember your numbers. Okay, so we have a copper pot, 2 kilograms, 150 degrees Celsius. 0.1 kilogram, 25 degrees Celsius. Okay, Jeremy?
2 kilograms, 150 degrees Celsius.
And this is our pot.
For the pot with the lid.
With the lid, yeah.
0.1 kilogram, 25 degrees Celsius.
Okay, so now we're going to combine these two things together. Right? These two systems are going to come into contact. This much water with this much. This is water. Should have figured out what this other element was. It's not pot, it's
It's copper, I think.
copper. Good memory. Okay, so now the amount of heat going into the water is the amount of heat that the copper pot loses,
Yes.
right? So Q, are the amount of heat that we're talking about being transferred around, is going to be equal to the mass of our copper times the heat capacity of copper times our final temperature, well, times 150 degrees minus our final temperature.
Yes.
That's the amount of heat going into the system.
No.
Or that's the amount of heat going into the water, I mean.
Yes.
From the pot to the water, this much. So now, our question is, if water is raised by this much heat, what temperature is the water?
Water is raised by that much heat.
Uh-huh.
Then it's 25 plus the T.
Well, we need to figure it out. So what's going to happen in this problem is our water, we're going to heat up our water to the point where it's boiling, and then we're going to convert all our water to steam. And then we're going to heat up the steam.
What?
What are we trying to find again?
Okay, so this is the Q. This is the Q from the pot. The Q from copper. I don't know. Q from copper. That's the heat going into the water.
Mm-hmm.
Now, we're going to have the heat that goes in, so the Q that goes into heating up the water is going to be equal to the Q that gets the water to boiling point. So the Q that gets the water to 100 degrees Celsius, plus the Q that converts the water to steam, plus the Q that gets water to its the steam to its final temperature T. All this water is going to be converted to steam, ultimately.
Well, how do you know the Q of your Q of T?
I don't yet. I don't know anything yet. I'm just laying out what we're trying to figure out. We're trying to figure out the final temperature that our water reaches. We're trying to find this T.
Your equilibrium?
Yes, our equilibrium temperature.
So why do you...
I'm just saying, here's what's going to happen with our energy.
Okay.
So as I pour that water into this pot, first my water is going to heat up.
Yes.
So my water is starting out like right here. First it's going to heat up to 100 degrees Celsius.
Okay.
Then it's going to turn to steam.
Oh, is that your Q of S?
Yes.
Okay.
And then it's going to heat up some more. So here's my Q sub T. I don't have great subscripts there. Here's my Q sub S. And then here's my Q sub 100, the amount we need to get to 100 degrees Celsius. Or we can say Q to get it to boiling point, Q to get it to steam, and then Q to get to our final equilibrium temperature.
And all three of those is equal to your formula up there?
And all three of those is equal to the amount of heat that the pot is supplying, that the copper is supplying.
Oh, because heat's conserved.
Yes.
Gotcha.
So we need to calculate each of these values now.
Okay.
So we already know what Q sub C is, it's that. So we won't bother with that for a second. But Q sub C is equal to, how much heat does it take to get our water to our boiling point? That is going to be the mass of our water times the heat capacity of water times our change in temperature, which is going to be 100 minus the starting temperature of our water, 25.
Oh.
Here's how much heat it will take to raise this much water up to boiling point.
Yes.
Okay.
Plus, the heat of fusion to convert the water to steam is going to be the mass of our water times the heat of fusion for water.
What?
Heat of fusion, that's just
Oh,
constant,
yeah.
Oh, your fusion. Oh, I see.
right?
Yep.
So this is converting the water now to steam.
Okay.
This was getting the water to boiling point. This is converting the water to steam. And then finally we'll heat the steam up some amount.
to 150 degrees.
No, to T, whatever our equilibrium temperature is.
Oh,
Because the pot's going to be a little bit cooler.
we're looking for T.
We're looking for T.
Gotcha.
Yes. So, N times LW, and then finally plus, we have the mass of our water times the heat capacity now of steam. I don't know if that's different from water.
Okay.
Might be the same as water, might be different. I'm not sure. I guess it's different. Times 100, or times our final temperature that we're looking for, T minus 100. Delta T.
Yeah.
Why is it T minus 100?
The final temperature minus the initial. Steam starts out at 100 degrees Celsius and then gets hotter
Gotcha.
to the equilibrium temperature.
Okay.
Okay, so now when we substitute this in for QC here, we have one equation with one unknown. T's are only unknown. Everything else we know. You can calculate this and you can calculate this.
Okay, I see.
Those are just numbers.
So it's just coming up with the fact that you needed to know
Yeah,
that.
I think that writing it out like this is the hard part of this problem, is seeing that. Seeing that you need to account for it going, heating up, going through a phase change, and then heating up again.
Yes.
Mm-hmm.
Right? Now, I already knew, well, we won't bother with that. That's what you need. And then you could solve it from there, right? You look up the values
Yeah.
and solve for T.
Are all these values in this chapter?
If you have to do ones with, going back to remember that we had,
The Young's modulus.
yeah, Young's modulus. So we had F over A was equal to negative Young's modulus alpha times delta T.
Mm-hmm.
So Young's modulus, you're going to have to go look up in chapter 11.
Everything else is in the chapter.
I think. There's a couple tables.
Okay.
So, and don't, remember, here we were using water. Only water freezes and boils at 0 and 100. If we were using liquid helium, then, no, not helium. If we were using liquid nitrogen, then the melting point of nitrogen is now negative 209 degrees Celsius.
209?
Yes.
Wow.
Yeah, you have to get nitrogen really cold for it to exist as a gas, or to exist as a liquid.
Liquid nitrogen.
Yeah, liquid nitrogen is absurdly cold.
What, don't they use something for with liquid nitrogen?
Yeah, just to cool something really quickly. That's what liquid nitrogen is used for. Flash freeze it.
Flash freeze it.
Uh-huh.
Spray some liquid nitrogen.
Or spray some on something to flash freeze it. Yeah. Liquid nitrogen is absurdly cold. At our temperature, it's not going to be a liquid, it's going to be a gas. So if I had a can of liquid nitrogen and I sprayed some out, that's going to quickly turn to gas.
Yeah, real fast.
And if it goes from liquid to gas really quick, it's going to absorb heat. That heat comes from somewhere. It has to come from the atmosphere around it. It's going to suck up heat out of everything around it.
Oh, that makes sense.
So yeah, you'll have a lot of the stuff in these tables. I don't know. Yeah, we'll call it there. If you get stuck on them, obviously we can go over any homework problems that you get stuck on.
Yeah.
Okay, so that's the end for today. We'll use the rest to talk about tests and then be done.